the code, but this is very initial simulation. We continue to do it. Yeah.
Thank you.
Yeah, we have still have 1 minute. Yeah, please. Okay.
We still not consider how to measure the fast boron, but we will consider it future. Yes.
Okay, thank you very much. Unfortunately, I have to stop here. Once again. Thank you. And I'd like now to invite on stage Professor Hyun-Jin Choi from the Korea Advanced Institute of Science and Technology that will give a talk on piezo-magnetic transformation for turning point perturbation implication to proton boron toroidal plasma. Professor Choi, the floor is yours.
Good morning. I'm Kyung-Jin Choi from Department of Nuclear and Quantum Engineering in KAIST, which is in Daejeon City in Korea. So today I will talk about isomagnetic transformation for turning point perturbation implication to proton-boron toroidal plasma. So I would like to say sorry because in terms of the volume, the main is not on proton-boron, but I believe that in the near future, it can be very useful also for the proton-boron toroidal plasma as an important application. So I prepared some basic knowledges, slide for the basic knowledge for someone who are not very familiar on magnetic confinement. So in magnetized plasma, the so-called mirror force minus mu gradient B, which has some analogy with the typical electric force minus electric charge gradient of the electric potential. So it has some analogy. So this so-called mirror force applies to a guiding center, which makes a specific particles trapped in a weak magnetic field region. So middle figures is showing the how it happens. So we can focus on the lowest order parallel motion for the simplest understanding. So here we have a mu b, which is indeed a perpendicular kinetic energy, which surprisingly behave as like effective potential energy in magnetized plasma, because here mu, the magnetic moment, is conserved in strongly magnetized plasma. So here B strength behaves the magnetic field strength behaves like potential energy. Mu is like electric charge, analogy with electric charge. So as a result, in the presence of the inhomogeneous magnetic field, we have this kind of effective potential wave due to the magnetic field strength. And then some particles which has some weak parallel kinetic energy, in the end, cannot overcome this kind of deep potential wave. And then as a result, it is trapped and then shows a bounce motion reflecting at specific points, which we call turning points. So by the way, in fact, this kind of description is based on the guiding center. Guiding center is the center of the gyro motion. So left figure is illustrating what's really happening to the real particle in the real space. So so you can see the deceleration as we go approach to the stronger magnetic field region, and in the end, it shows some reflection and shows a bounce motion. So in toroidal magnetic fusion system, we have, due to this kind of donor-like shape, we basically intrinsically have this kind of inhomogeneity of the magnetic field in the poloidal angle direction, just like this. This is a very intrinsic one for the toroidal system. And then as a result, if we see the poloidal cross-section, if we cut with some specific toroidal angle, we can see this kind of banana-like shape of the trapped particle orbit. So indeed, we call it banana orbit. So you can see from these two arrows, you can see that, oh, okay, to the lowest order, indeed, we have a parallel bouncing motion. Here, the poloidal angle direction is representing the parallel motion. Parallel means along the magnetic field. And then in addition to this poloidal angle motion, we find that there is some radial motion because we have some finite width of this banana. The reason why is because of the higher order perpendicular drift of the guiding center. So here, mainly due to the basically due to gradient B drift. So right figure is illustrating why we have this kind of perpendicular drift in the presence of inhomogeneous magnetic field. So here, this red ones are illustrating the inhomogeneous magnetic field. And then please recall that the gyro radius, the Ramu radius, is inversely proportional to the magnetic field strength. So, let us start with the weak magnetic field region. Then we have a large gyro radius. And then as we approach to the stronger magnetic field region, the gyro radius decreases. So we have a smaller orbit. And then as we go back to the weaker magnetic field region, the gyro radius again increases. So this repeats. So as a result, we have a perpendicular gradient B drift in the perpendicular direction. So these are the basics. And then in toroidal fusion plasmas like tokamak, spherical tokamak, stellarator, we need to calculate various long-term phenomena which are slower than the bounce motion of magnetically trapped particles, the banana particles. And then therefore, for an efficient calculation, various cores use bounce average defined like this in a mathematical sense to focus on the long-term dynamics. So looking at the denominator of this definition of the bounce average, we can realize that, so by the way, here S is nothing but the location on the magnetic field line. So it's a parallel length, and then V parallel is of course the parallel velocity. So one can realize that this denominator is nothing but a period, one period that the time it takes for one bounce motion. So then from that, one can realize that this bounce average is indeed a weighted average of specific quantity, considering the property of the bounce motion. So here I presented some single particle long-term dynamics, slower than the bounce motion. So one example is it is the precession of the bounce center in toroidal direction in the case of tokamak. And in the case of stellarator, it's more complicated. So some particle just in this cross section just remains in banana, and some particle shows a much larger banana, which is called super banana. Some particles just go out as a result of secular radial drift. So these are single particle view, but in reality, we have a more important phenomena, which are collective phenomena, long-term collective phenomena, slower than the bounce motion. So an example of heating and current drive, another example is transport, and also we have energetic particle physics. So for the heating and current drive, codes like CQS3D and Loop uses bounce average like this for an efficient calculation. So they are bounce average Fokker-Planck codes. For the case of transport, an example is Knossos, which calculates the Neophysical transport under 3D magnetic field. For the case of energetic particle physics, Orbit and Nova K for the alpha and eigenmode stability calculation often uses bounce average for an efficient calculation. Okay, next I would like to introduce the magnetic perturbation in toroidal fusion plasmas. So in many cases, by the way, it is convenient to conceptually distinguish a desired magnetic field configuration B0 from the real one, just B, thereby treating the deviation from the ideal configuration B1 as a perturbation. And there are two practical examples. One is in tokamak, the other one is stellarator. So in tokamak, we pretty often apply so-called resonant magnetic perturbation, RMP, intentionally to control the, so we intentionally slightly break the perfect axis symmetry of tokamak magnetic field to control the confined plasma. And then in the case of stellarator, we basically, nowadays, everyone is talking about the optimized stellarator. The optimization, the term optimization is used because we cannot, in reality, realize the perfect symmetric or isodynamic magnetic configuration in stellarator. So as a result, we need some kind of breaking, some deviation from this perfect configuration. And then we need to choose we need to determine which places are very important, so that we need some proxy to this perfect symmetry or isodynamicity, and which locations are less important, so that we can make some significant deviation from the ideal configuration. So we need to choose that, determine that. So that's the reason why we use optimization, the word optimization for the stellarator. So the left two figures are examples of quasi-axis symmetric configuration. Right two are examples of an example of quasi-helical symmetric stellarator configurations. So in summary, the magnetic perturbation is the concept of magnetic perturbation is widely used in present-day toroidal fusion plasmas. And then with this magnetic perturbation, the energy particle loss by that is a crucial issue in tokamak and spherical tokamak, because RMP is one of rare actuators together with neutral beam, radio frequency wave, pellet, and gas pulp to control the confined plasma. And also the degradation of the energy particle confinement by the intrinsic error field is also an important issue here. Error field is due to the engineering error, human error. And together with that, the so-called neoclassical toroidal viscosity due to the 3D field has also been considered as an essential piece in the effect of magnetic perturbation. And these also set severe constraints also in designing the stellarator and magnetic configuration, not only for tokamak and spherical tokamak. So in the end, the point is that the calculation of particle motion under 3D magnetic perturbation is crucial for the toroidal fusion plasmas. Okay. Then, so then we want to calculate the some dynamics lower than the bounce motion by calculating the bounce average that I showed in the previous slide. And then we have an issue which is due to the turning point perturbation. So in general, of course, the turning points of the bounce motion should also be perturbed in the presence of the magnetic perturbation in general. And then And meanwhile, the perturbative treatments of the bounce average has been employed in various analytic theories and numerical calculations to ensure the regularity of the orbit calculations in the presence of the complicated magnetic perturbation. So because the magnetic perturbation can be very complicated, so very complicated structure. So in the cases, the calculation of the exact bounce motion can be too challenging. So in such cases, many people chose perturbative treatments of the bounce average to ensure the regularity of the bounce orbit in their calculation. Okay, then if we try a systematic perturbative calculation of the bounce average, including the turning point perturbation, this is the full expression of the bounce integral in the bounce average with the perturbed turning points. And then first step should be dividing this integration range into three parts. So one is the along the unperturbed bounce orbit, and then the other two are the deviations from the unperturbed bounce orbit due to the turning point perturbation. Of course, there can be some further procedures for perturbative treatment, but this should be the first step. And then many researchers has focused on the first one, basically. And then we have a serious issue in calculation because in this case, in the first term, in general, we can have an artificial imaginary V parallel velocity. Because so parallel velocity can be expressed by the square root of the total energy minus perpendicular kinetic energy minus potential energy. And then near the turning points, since we are treating the unperturbed bounce orbit while considering the exact V parallel, in the end we have near the turning point where the V parallel is very small. I mean where the mu v plus E phi and the total energy are very similar with each other. There can be some small artificial imaginary V parallel. And then some of you who already have some knowledge on this kind of this kind of track particle calculation in the presence of Magnetic perturbation may recall the concept of Lagrangian perturbation, which has been developed by suggested by Alan Guzer and extensively used. The point is that point of this concept is that we move back from the perturbed magnetic surface onto the unperturbed magnetic surface, and then we modify the magnetic field strength perturbation to the Lagrangian form. So now we have an Eulerian part plus the additional part from this kind of transformation from perturbed magnetic surface to the unperturbed magnetic surface. So the deviation is characterized by this displacement vector chi. Psi. So, but this Lagrangian perturbation concept still cannot resolve this issue in the calculation, because still there can be some inversion of these two vectors near the turning points. So this is a serious calculation issue, basically. Okay, so motivated by this, to provide a systematic perturbative calculation of trapped particles, we have developed the retransformation theory of the bounce orbit rectification from complicated magnetic field to a regular ideal desired magnetic field. So the key point is that we introduce systematic mapping from original guiding center space to a new phase space, which satisfies this kind of energy conservation. So this expression is very typical, right? The typical energy expression. And then the right one is our desired expression for the total kinetic energy. Total energy. So we have a typical parallel energy, kinetic energy, and then we have a perpendicular kinetic energy, and then we have a potential energy. Looks fine. But the point is that we have zero here, and zero here for the fields in the new phase space. So that's the reason why so it means that when thinking about the energy and also the parallel velocity, we don't need to worry about the perturbation of the magnetic field and also electric field. So that's the reason why I call why I said it's a kind of orbit rectification. So we call this mapping as an isomagnetic guiding center transformation. Okay, so I can skip all the details of ordering. So here I would like to present a brief introduction of the retransformation technique, some key points, which is pioneered by literature and extensively applied for systematic guiding center and bound center descriptions. So the philosophy is that we a priori, at the beginning, consider a specific form of the desired Lagrangian, the Lagrangian that we want in the end. So so I just wrote a very abstract form, but we can think about specific form for this P and also this Hamiltonian H, and also corresponding new phase space variable C bar. So for example, so this retransformation technique is a very general framework, mathematical framework, and then it has various applications. So for example, in Serdan guiding center description, I should say gyro center description, we desire a well-conserved magnetic moment in inhomogeneous background magnetic field and also in the presence of time-varying turbulent fluctuation by the use of this simple form in the symplectic part for the action angle variable of the gyro motion, and also this kind of nicely defined first order Hamiltonian, which contains the gyro averaged turbulent potential. So we set all the desired result, and then we already know the original setup, and then we bridge the Lagrangian and the variables that we want to the original ones. by the use of Lie transformation, like this. So this is the key point, first key point. And then here T and T inverse are the Lie transformation operators called pullback and the push forward operators. And here S is just the gauge function, familiar one, that we already all know in the Lagrangian calculus. And second key point is that we consider near identity Lie transformation and perform a perturbative analysis by decomposing the whole operator order by order by this kind of expression. So here ln is the nth order Lie derivative. When applied to the Lagrangian one form, it has expression like this. And then what is Gn here? Gn is the nth order generating vector field, which originates from which means nothing but the difference between the original phase space variable and the new phase space variable. So simply the difference of the two. Okay. So and then if we apply this kind of perturbative expression of the operator to this, the full expression for the Lagrangian transformation, we can obtain order by order equation like this. You can obtain this simply. And then we substitute the explicit expressions of the desired Lagrangian and the original Lagrangian. And then as a result, we can obtain the order by order expression of the generating vector field, thereby completing the establishment of the transformation. So this is the procedure how we construct the transformation framework. So I will skip many details. So for the isomagnetic guiding center transformation, we desire this kind of Lagrangian with only with unperturbed magnetic field and also unperturbed electric field. So this is what we desire for the rectified orbit. So in the IGC space, isomagnetic guiding center space. And after some calculation, in the end, we can obtain this kind of expressions for the non-zero component of the generating vector field. So one important point is that in addition to the configuration space, we need a transformation of the variables in the parallel velocity space. So it means that any kind of transformation only considering configuration space is not systematic. So we definitely need this kind of transformation in phase space, not only in the configuration space. This is one important message. And then together with, by the way, we can see that in the expressions of the generating vector, which means the difference between the new variable and old variable, we can see S1 here, S1 and S1. So what was S1? S1 was the gauge function in the Lagrangian. And then we can also obtain the equation which determines this gauge function. So which is written like this, pretty simple. So the unperturbed propagator ddt and then the gauge function equal to the effective Hamiltonian. So this is normal Hamiltonian part, perturbed Hamiltonian part. And then we have some special part which originate from the simplex part in the Lagrangian. Okay. Oh, okay. And then next, based on the completely rectified bounce orbit in isomagnetic guiding center space, we further perform the isomagnetic bounce center transformation because our final purpose is to obtain the bounce average orbit of transferred particles. So I will skip all the details because this procedure is identical with the well-established previous works. So as a result, we can obtain the IBC Lagrangian like this. And then I would like to emphasize that in the Hamiltonian, we systematically include the orbit squeezing term from the finite radial orbit width. Okay, I also prepared some explicit derivation, general heuristic but general derivation of the orbit squeezing factor, expression of the orbit squeezing factor, because the previous theories only consider the specific magnetic configuration, but okay, I was able to obtain this kind of more generalized expression for the orbit squeezing effect. So in the Lie transformation technique, this orbit squeezing is represented by the generating vector in the radial, here vector is radial direction. So we can see the orbit squeezing vector S, which is larger than unity. So this generating vector is definitely smaller than the reference case without any shear of the radial electric field. So here my new point is K0. So I obtain a more generalized expression of K0. And then, by the way, so maybe I was happy because I thought that I to construct all the nice Lie transformation framework to rectify the bounce orbit. But I realized that in a specific case, my framework has some problem. So we should go back to the equation for the gauge function, which determines all the transformation. And then we find that with Fourier representation in the binomial angle and the bounce angle, we can obtain the formal solution of the S1, the gauge function that we want. And then I found that if the denominator is 0, I have problem. We have singularity. So this condition is a resonance condition, of course. So this is more precisely drift bounce resonance condition. So I further modified my transformation to systematically include this resonant particle effect. And then the point is that simply for the resonant component of the magnetic perturbation, I didn't do any transformation. So that's the key point. And then as a result, how we describe the resonant particle, then with the use of the slow phase angle defined like this, here N0 and L0 are the specific part of the resonant component. And then we can describe the dynamics of the resonant particle, bounce average dynamics of the resonant particle with the use of this slow phase angle in a very compact form, together with the effective Hamiltonian. And then, by the way, this is not the all, because if we combine the perturb field effect to the original equilibrium field effect using the Hamiltonian, and then after standard procedure, we can find that the resonant particle shows this kind of phase space island structure in the slow phase angle and the conjugate action space. And then again, after some standard calculation for the O point and X point for the phase space island, this is very typical one. Considering that they are fixed points in the island, then I was able to obtain some generalized expression for the super banana radial width. So this is an example of the super banana width, radial width in the lowest order. Okay, yeah. Okay, so I have to emphasize this part, but so anyway, so let me explain briefly. So in proton boron plasma, we have a mega electron volt range proton and energetic proton and fusion alpha. So they have very large banana orbits. So we need a very precise, careful perturbative treatment of the energetic proton and fusion alpha in proton boron plasma. And then I found that this special term for the effective Hamiltonian, which is very important for the super banana orbit resonant particle. This kind of very special term coming from the kinetic correction and of this effective Hamiltonian can give a significant impact, especially for the proton boron spherical tokamaks, where we have an inverse aspect ratio and approach to unity. Okay. So this is summary. So yeah. So we developed Lie transformation theory for systematic reduced restriction of the trapped particle in toroidal fission plasmas in the presence of magnetic perturbation. So we resolved the calculation issue in the bounce average due to the turning point perturbation by rectifying the bounce orbit through isomagnetic transformations. So our theory reveals that bounce drift resonant orbit needs a careful treatment, especially for the fission plasmas having large portion of mega electron proton and fusion alpha. So, and our theory generally includes the squeezing effect of the banana orbit. And then, so the applications of our theory to various calculations are very welcomed. Thank you.
Dr. Choi, for this still a complicated thought, if I may. We have still a time for one, maximum two questions. Yeah, I see Martin.
This work is pioneering.
Thank you.
It answers the question that some of us have always been thinking about. How do you combine the complex coordinates, simplify the coordinates, and then deal with turbulence, and then deal with the discrete orbits.
Mhm.
So maybe my question is very simple. You talked about orbit squeezing, and you mentioned the original simpler ideas about orbit squeezing. And then you said that the orbit squeezing, that's only part of the mechanism. There's the other part. Could you explain what is the physics of the other part?
So I guess you are asking about the effective Hamiltonian, I guess.
That's right.
Yeah. So this part. So this effective Hamiltonian, in the end, for the non-resonant particles, they are one can treat this as just some kind of dummy quantity, which only appears in the transformation. So if we really want to calculate some secular motion of the non-resonant particle, then in the end we don't see effective Hamiltonian. It's the form of the non-resonant particle dynamics is a very standard. So it's just a typical product grad B drift and the equals B drift. So we are just happy. But for the case of resonant particles, we need to consider the effective Hamiltonian. So the physical reason why is because it's resonant particle. So just like when you think about the Landau damping and resonant particle, for resonant particles, these kind of fields are just DC. It behaves like a DC. So for the non-resonant particles, this the contribution of this special term disappear after bounce average because it acts like a AC field. But for the resonant particles, it has a clear DC component. So that's the reason why we should think about this special additional contribution in effective part of the Hamiltonian, even after bounce average.
Well, thank you.
Yeah. Very quickly, if it is brief.
The brief question is, since you mentioned that when this RNP can work well with for the energetic particles, since you know that in PV system the particle energy is higher, this means that we can reduce the request for the amplitude of RNP for the PV plasma.
You mean we can? So I think that this calculation is so the EP loss due to the RMP, in fact, it gives a severe constraint for the maximum amplitude of RMP that we can use. So this is a problematic issue basically. So and then by the way, so basically with RMP we expect bad. I mean in terms of the bad effect in terms of the confinement, EP confinement, but there is a further advanced discussion on the RMP is because if there is with specific RMP configuration, maybe we can minimize the EP loss while maximizing the outer transport of the ash of the undesired elements, which originate from the, for example, fusion reaction. So like, for example, the helium ash in the case of DT fusion. So there are some advanced discussions on that. So maybe we can use RMP for take some advantage.
Yeah, thank you. I am afraid we are ready to stop here. Thank you again, Professor Tree, the presentation and the pleasure to give the floor to Professor that will end on efforts towards a multi-scale simulation framework for laser fusion. Professor Wood, the floor is yours.
Okay, thank you. Okay. Okay. Good morning. It's a good honor to give the speech here for the first time. And I'm Wudong from Shanghai Jiao Tong University. I will give
brief introduction of our recent work. Just not yet complete, but we have some progress towards a multi-scale simulation framework for laser fusion. The simulation of laser fusion is not that easy. It involves a very complex coupling of multi-scale spatial and temporals. Just take double cone ignition laser fusion for example. In this compression process, it's a nanosecond scale, and we need I in for our have influence on the electron eye temperature relaxation and many others. So to calculate the collision frequency, we need this one, the Coulomb log. Now, how to calculate this Coulomb log? Typically, we need this collision cross section, right? Collision cross section. We need this one. But how we calculate this one? We assume that the potential is the bi-screened potential. The in plasmas is the bi-screened potentials. But the bi-screened potentials only works for some very weak coupling plasmas. But in laser fusion, the density changes several orders of magnitude, and the temperature also changes several orders of magnitude. So we have some reasonable strong coupling and also moderate coupling. So this weak coupling model is not correct. So maybe it's not correct. So we need a more accurate evaluation of the potential. It's not just Coulomb spin plasmas. So this is why we need atomic code. And the other example is that, for example, in the design experiments, if we want to know the density and temperature of the plasma, we usually use some X-ray backlighter. This is an image of X-ray backlighter. So we use this equation, and this equation is absorption of this X-ray backlighter, and the absorption depends on this one. This one is plasma opacity, and this one depends on the plasma error density. So this opacity can only be given by atomic code. It's atomic code. So this is why this is also why we need this kind of calculation. Now, how to do that? Our starting point is we need a very fast, efficient atomic code. And this code can easily compile with our big code, with our fluid code. We need a fast one. And so we use this average atom model. So the average atom model is easy to understand. So now this is plasma, and consider of a lot of ions surrounded by electrons. So we just pick one ions with a sphere, and the radius of this sphere just depends on the plasma density. So we just solve this atomic sphere. So now the potential now is not just Coulomb screen potential. Its potential include this one is Coulomb force, and this is electron interactions, and this is some exchange coupling interactions. So our aim is to solve this potential. Now, how to solve that? Suppose we already know the density, and then the density will influence its potential, and the potential will then obtain calculates the electronic orbitals, and the orbitals will then determine the density. So it's just the density function theory framework. So now this is the basic idea, and now this code we also already have completed in the last 2 years, also by our students from the very beginning, and now the name is Physics. This code now includes the solution of string equation of atomics in plasmas, and now based on this wave function, we'll calculate opacity, equilibrium states, and also some scattering information of plasmas. Okay, now we actually give some results. This is a cross section of alumina with density over this and temperature over this. We find that our results have good consistent with data from a Livermore National Lab, and so this compression, and we can also calculate some key inch. This key inch of some metals also can be used for the diagnostic of plasma. And now we can find that this ES energy will change in different temperature and density. And our results also have good consistent with the Livermore data. And also have this year. From the very beginning, we developed a code. Okay. Now I will give some very brief introductions of what we have done using our current simulation framework. Okay, so in the double cone ignition laser fusion, if we want to diagnose the density, temperature, of this DT of this fuel, we use X-ray time scattering, and we use this DFT theory to figure out this experiment spectrum data, and finally, this we can successfully infer that the temperature is this one and the density is this one. Now this paper was just published last year, and we can use our simulation framework to very seriously study the compression ratio of some high density plasma jet. And so because in this double cone ignition, there is a cladding process. Okay. And all so already um, the Okay. Uh,
multi be the solution to the shaping equation or as different module.
You mean this one?
Yeah, it's two.
Oh,
You have two.
okay, that's
The three functions should
Okay,
come from.
okay. Let's give a brief introduction. This is a for the solution of three equation, and why there is wave function model, because this wave function, in order to solve this wave function, actually there are many methods. So we usually expand the wave function in use some for 样条差值，或者是其他的有好几种对波函数展开的方式。样条差值的计算量小，但是精度差。像那种格点展开，计算量大，精度高，所以它会有一个专门的模块去存储这样一个 wave function 的。OK。
Yeah, okay. I am not sure for the action. But I understood that you perform an expansion of the wave function over a certain basis. Okay. Okay. Perfect. I think we have to stop here now. Thank you very much. And we thank you again, Professor Dong, from Shanghai. And now we should have on the program a little poster flash talks, which I don't know, I'm not sure, but yeah, I have to moderate it. So I hand over to you. Okay, thank you.
We will have three short remarks on this session, until 5 minutes of each. So,
Yeah.
I agree. The and uh,
The magnetic coils. For the laser diagnostics, we have the interferometer. We actually have two of the system. One is the HCN laser system, and another is the CO2 dispersion laser system. The second one is currently under construction and commission this campaign. So I think it will be online in the next month. And for the electron temperature and density, we use the Thomson scattering system, which the laser is launched from the lower bottom of the device, and then we can collect the scattered laser in the mid plane here. This one is for the visible spectrum. We can monitor the impurities and the ion temperature by this two system. It has two spectrometers. And this is the crystal X-ray crystal spectrometers. It can be used to measure the ion temperature, basically in the and the rotation velocity in the core region. We also have the microwave reflectometry. It is a FMCW system, so it can measure the density profile from the edge to the core, and also it can and also we have another one in the just in front of the ICF antenna, so we can measure the density in the front of the antenna. And we also have the diverter probe system. It is for the previous plate diverter, and in the recent V-shaped diverter, we also design and installed the similar system. We also did some integration for the different diagnostics. So you can see here we use a trapezoidal cavity that can integrate several spectrometers in one port. So this will be very important for our next machine, since the diagnostic port is very limited. Yeah, basically this is the XUV array, and to measure the radiation power, and this is the hard X-ray array to measure the energy of the runaway electrons. We also have the multi-band filtered spectroscopy to measure to measure the image of the struck point, which is shown here. And this is basically the current arrangement of our all our diagnostics. So now we are busy working on the diagnostic systems for EHL2 Spectrotorus, and this experience will help us to build the systems for our next machine. Yeah, thank you.
And the coffee break is waiting for us. Please come back at around 8. Thank you. Set for all the speakers.
那鲍总问的那个问题，
Yes. Yes.
不是让你解答，这个应该 要艾特一下对方，或者咱
I don't feel 生技术就发挥了重要作用。
为了打造这台硬核装置，中国科学院近代物理研究所的工程与科研团队率先开展了基于数字孪生驱动的大科学工程建设新模式。科学家们在电脑里先造了一个虚拟的强流重离子加速器。
Our first speaker is Cheng Rui from Institute of Modern Physics. The title of his presentation is Heavy AI Beam-Driven HEDP Research. Okay.
Thanks, Chairman. So, this VCR just shows our new facility. Why I show this? Because yesterday just finished the final acceptance inspection, and now it enters the beam operation phase. So today I just want to show you the new progress of high beam driven high density physics research at this facility. Just
那什么是重离子强流重离子加速器装置？
First of all, I would thank our collaborators, especially from GSI and Xi'an University and Peking University and the Laser Fusion Research Center. Without your help, we cannot achieve this progress at all. And in my talk, I will show you the progress of health and the HEDP preparation work and the preliminary investigation at the Lanzhou facility. Finally, summary. Okay, we come together for the controlled fusion energy. It is expected as the ultimate energy form for the human society. And since 2022, American NIF announced the first time it got energy gain over than one. So it attracts global interest. And in these years, they achieved 11 ignition succeed, and the energy, produced from the IP
7 MeV excitation energy in the carbon 12 nuclear. And then we introduce the high nuclear moment pair. This configuration is very difficult, is very suitable to describe the shell-like structure at the ground state and the low 9 state. And then we can also introduce the 3 nucleon clusters such as the helium-3 or Triton nuclear clustering structures. We can describe the higher lying energy structures. So, but there has a challenge for our calculation because we want to optimize the generated coordinates and the spin and the high nuclear moment pair together. There means the amount of calculation. So another challenge is the Hamilton effective Hamiltonian. Because of we know if we want to calculate the high energy excitation states, there is a less understood area. So how to choose and determine the wide Hamiltonian is very difficult. But how to address these two challenges in our work, we want our solution is use the artificial intelligence method to solve these two challenges. Start from our theoretical models. That has a mistake. Microscopic reflection and the effective Hamiltonian, and we propose two neural network. One is to optimize the reflection. We name it a control neural network. Another is we optimize the effective Hamiltonian. We name it a Hamiltonian generation neural network. We combine with the theoretical model and our AI intelligence, and then we can consist with the experimental data from the large scale facilities. We use the experimental data to training our two control neural network. We can to realize the optimization for the reflection and Hamiltonian together. And the first agent is the control neural network. Use the carbon 12 nuclear for an example. The left figure shows the structures of our network. The input of the network is the generated coordinates and the generated coordinates for the 3 alpha clusters. This is carbon 12 nuclear reflection. And also we input the intrinsic energy for the set of bases. And then the output is the charging amount of the generated coordinates. And we can use the basis to calculate the physical properties such as the radius, the rotational symmetry, and the intrinsic energy. How to train our neural network? We use the loss function. There is the 3 atoms. The first atom is the intrinsic energy. We can use the intrinsic energy to realize the energy variation. And the second atom we can use to realize the space constraint, such as if we want to get a compact structure and the bigger radius structure, we can use the second atom to realize this process. And the third atom is very important for our calculation because we all know for different state there has a different angular moment. So if we want to optimize the reflection and the different angular moment, we can use the third atom to realize the constraint. Here we set the angular moment equals 0. If we want to calculate the 2 plus or 2 magnitude state, we can set the angular moment equals 2. And the second agent is our Hamiltonian generation neural network. Based on the known experimental data, we use the AI logarithm. We can learn the physical properties information from the experimental data, and then we can use the experimental data to train our neural network. And then we can get the available Hamiltonian to describe the physical properties in the high energy area. And combined with the agent 1 and agent 2, we can get the 2 agent coupling framework. The first agent is used to optimize our reflection, and the agent 2 is used to fine-tuning the effective Hamiltonian. We can continue to feedback them together, and then we can optimize the reflection and Hamiltonian together. And how how they work. Sorry, this video shows the evolution of the 3-alpha cluster states in carbon 12 nuclear. This is the imaginary time evolution for the different 3-alpha clusters. And you can see there we get the different configurations such as triangle and optical angle, beryllium and helium-4, linear chain and gas stack configurations. And there shows the energy variation. We can start from the high energy and through the continuous network to optimize the wave fraction. We can get the low energy structure, no energy result. This is the energy variation, and our result will get the lower energy compared with the other calculation. There will shows that our calculation will get the more close to the solution for the effective Hamiltonian. And here, if we want to calculate the alpha decay process in the carbon 12 to the alpha plus helium 8, we can get the beryllium 8 to alpha clusters reflection. And also, we use this reflection to do the benchmark in the carbon 12 nuclear. And this is the rotational band calculation. As you can see this figure, our calculation will correctly describe the order and the positions for the known energy Brood threshold. And there is interesting things because of as the excitation energy further increases, what happened will emerge here. In many previous work, the experimental and the theoretical calculation, they all study the energy below the 10 MeV. They find many structures such as alpha plus neutron structures behind under the 10 MeV. So if we want to study the high energy area, we need to explore and understand what is the structures at this area. In our calculation, we found there are the alpha cluster bring up and another triton structures recombination. And how to explain this process? If we start from the to alpha to proton wave fractions, how to get the alpha plus to triton wave fractions? There will through two stages. The first stage is the one alpha cluster break up. Will get the triton plus proton, and then this two the neutron plus proton will get the new triton clusters. This is the this is the case in the beryllium 10. And there has a very similarity things in the carbon 12 nuclear. If we want to study the high energy states in the carbon 12, there may be has the same alpha brink case in here, but in this case there will has two types two types of reflection. And for the proton plus Boron11 fusion through calculation, the next report from Zhou will show it for us. And there is another case in the beryllium-9 and the boron-9 calculation. We also find that at the high energy area, the two types of reflection will contribute both important in these three states. So if we get the wave fraction, we can use the relative wave fraction to calculate the decay width. As you can see, this part from our microscopic wave fraction, and with the unmeasured theory, we can calculate the decay width. And there is interesting thing is that if the structure is very different, the relative reflection is also different. As you can see, the red line and the blue dashed line, the amplitude and the amplitude and the position of the peak is very different. For the relative reflection, we can calculate the decay width. As you can see, the decay width, this configuration is 19 keV, and this configuration is 34 keV. This is very different for the decay width is very different because of the configuration is different. So use this theoretical framework, we can do another calculation, such as in collaborating with Professor Yan Li at Peking University. We calculate the carbon 12 nuclear use this same framework. And here I want to show the Hamiltonian generation neural network. This line shows the experimental data, and this line shows our theoretical calculation. As you can see, there is a very good agreement with the experimental data. So this Hamiltonian is reliable to describe the properties in the carbon 12 nuclear. And sorry. And also, we, in collaboration with Professor Xin Xu at Institute of Modern Physics, we calculated the 3.5 minutes at 8.08 MeV. This is very interesting because of the experimental data. They uncovered two decay channel. It's very important it's all very important in this data. This one is the proton emission and another is alpha decay. This state is very similar to the intermediate, the key intermediate state in the proton boron-11 fusion in carbon 12 nuclear. And in this framework, we can calculate the proton emission and the alpha decay. Use one wave fraction together, and also we can consist with the experimental data. Yeah, okay. And I would like to summarize my calculation. Under the grounds, you can get the shell structure and molecular structure, and the low energy low energy state, we can get the shell cluster coexistence, and the higher energy threshold will get the BEC or the linear chain structures. But in the higher excitation area, there will happen the alpha cluster bring up and the recombination will happen. So maybe this configuration will improve the variable inset for the proton boron-11 fusion calculations. And this is the last of my poster. We want to combine with the theoretical model, our theoretical model, and the AI agent, and we hope to learn the experimental data to training our AI agent and use the framework to calculate the proton boron-11. And the next report will presented by Fang Zhou. He will introduce our recent work in the proton boron-11 fusion calculation. Thank you very much for your attention. This is all my presentation. Thank you.
Okay, very nice talk. I have two questions actually. One, you are using some AI Hamiltonian as well as the wave function and a model to calculate some nuclear with cluster structure. So, do you have any assume the form of your wave function? So it's just like a web packet, or you should borrow some base for this wave function calculation. And second is, how do you you have proven two-body, three-body? So as we know, we have a lot of symmetry we can apply into the Hamiltonian. So do you have any assume the form, the wave function as well as the Hamiltonian?
Okay, thank you for your question. Yeah, it's very important for our calculation. The AI method for our calculation, we actually the reflection is very suitable to adjust, because in this calculation we use the three-body reflection, but in any other for other nucleons such as maybe oxygen 16, neon, 12, we can see the reflection to the full body or cell body. It is very easy to realize. And for the Hamiltonian, you know, we know the Hamiltonian. There has the different atoms for the different atoms. Because of our Hamiltonian has some adjectable parameters, such as there has some adjectable parameters. How to choose and determine the Hamiltonian is very difficult. So we can learn. We can from the experiment data to training our Hamiltonian generation neural network, and then we use this method. We can choose what is the parameter is very suitable for our calculation. We can use our AI to learn the properties from the experiment data. So
Do you perform any test if you neglect one term or two terms of other Hamiltonian? So what the result will be?
Oh, maybe so sorry. Maybe we can take the current break. Thank you for your question. Thank you.
Thank you for the talk, and I see it's a very powerful method. My question, and you demonstrated the Hoyle states, which is very important for us. Otherwise we wouldn't be here. But my question is, have you predicted any state that it has not been known before? I'm asking this question because I'm still looking for methods to produce boron-10, maybe in neutron star mergers. These models that they have produce the peaks very well, but at carbon and beryllium and all these things, they are not good enough. So can you predict something that we do not know already?
Oh, okay. Okay. No, what here? Oh, okay. Actually, the next report, Fang, sorry, for Fangzhou, he will show the proton boron in heaven. Thank you.
Question. So the last speaker this morning is Fang. So also from Nanjing. The title is Key Immediate States in the proton boron fusion research reaction. Okay.
Sorry. 这个是激光。哦，这个。OK。
Good morning, everyone. My name is Fang Zhou from the Nanjing University of Aeronautics and Astronautics. Today, my title is Key Intermediate State in the Proton-Boron Fusion Reaction. Okay, as we all know, the proton-boron fusion is a hot research topic right now, with important applications in many fields. First, in terms of energy, the raw materials are abundant in nature, and the reaction produces no high-energy neutrons, so it has huge potential to become a clean fusion energy source. And secondly, in medicine field, we know that the neutron boron capture therapy is well developed in Japan. So we can follow in the same logic. That means we inject the boron-11 targeted drugs into cancer cells and to use a proton beam to trigger the fusion. Then the release the alpha particles will kill the cancer cells. Yes. Okay, this figure is showing the reaction mechanism of the fusion. Before the incident, proton react with the boron-11 nucleus, it must cross the Coulomb barrier. However, we can see the kinetic energy of the proton is not enough, so it must rely on the quantum tunneling. usually the chance of this happening is extremely small. So the fusion only happens when the total energy of the proton plus boron-11 nucleus exactly match the energy of a special highly excited state in the carbon-12 nucleus. After the proton and the boron-11 interact to form a highly excited carbon nuclear, carbon-12, it first decays into primary alpha particle and beryllium-8 nucleus. Then it decays into two secondary alpha particles. We can see there are two channels, the alpha 1 channel and the alpha 0 channel, corresponding to the 2+ state and the ground state of beryllium-8. And in our research, we mainly focus on this key intermediate states above the proton plus boron-11 threshold. And the formation of these states is crucial for the fusion reaction. Experimentalists began exploring the proton-boron fusion reaction as early as the last century in 1987, as shown in the left figure. Becker performed the first experimental measurement of the reaction cross-section. As you can see in this figure, at the 620 keV, the resonance peak, this peak is dominates the overall cross section, and the main contribution on this peak mainly comes from the alpha E channel, and its final state is the 2+ state. Later in the year 2000, Nevins fitted the previous experimental data, and he obtained the curves of the S vector and the cross section. Today, we still use these results. Look at this figure. We can see that the first two resonance peak exactly match the first two highly excited states above the proton plus boron-11 threshold. We all know that the resonance peak in the low energy region is valuable, but recent data in the low energy region possesses significant uncertainties. We can see in this figure, and it heavily relying on fitting and extrapolation. So theoretical work is urgently need to clarify the fusion reaction rules in the low energy region. And because the S vector only depends on the internal structure of the nucleus, so it is important for us to calculate the accurate wave function of the carbon-12 intermediate states. So to do this, we need the wave function of the boron-11 ground state, the intermediate state of carbon-12, and the 2+ state in beryllium-8. Previous studies have shown that the boron-11 has an alpha plus triton configuration, and our group's previous work also found an alpha plus alpha configuration in the 2+ state of beryllium-8. However, the theoretical investigation of the carbon-12 in its highly excited state remain unexplored, and that is what we want to investigate. Here, in our group's previous work, we calculate the energy spectrum of the boron-11 nucleus below its alpha plus triton threshold, and the result is consistent with the experimental data. We also calculated its ground state's special distribution. This could be used. This could be the input for our reaction calculation. In our previous work on the beryllium-10 nucleus, we used an AI-driven dual agent coupling method to explore its highly excited states. around 17 MeV, the alpha cluster breaks up and triton clusters begin to emerge, which is so different from its ground state. And this inspired our ideas about the structure of the intermediate states of carbon-12 nucleus. We can see the theoretical research on carbon-12 has primarily focused on low-lying excited states below 14 MeV with an isospin T plus 0. But the key intermediate states of carbon-12 that we want to explore is located at higher energies above 16 MeV with an isotope T plus 1. Based on the alpha cluster breaking phenomenon we found in the Brilliant 10 nucleus, we predict that the same cluster breaking phenomenon may also exist in the intermediate states of carbon-12. Experimentalists suggest that boron-12 contains isobaric analog states corresponding to these two key intermediate states in carbon-12. And also, previous studies have shown that these two low-lying boron-12 states have an alpha plus triton plus neutron configuration. So in order to improve our computational efficiency, we first calculate the isobaric analog states in boron-12. Then we use isospin substitution and isospin projection to get the total wave function of the key intermediate states of carbon-12. Here is our nuclear wave function. Our single particle wave function is a Gaussian wave packet, and our alpha cluster wave function is two antimaterizing two protons and two neutrons. Then the wave function of this nucleus consists of alpha clusters, triton clusters, and two kinds of nucleons. Finally, we calculated the energy using generalized eigenvalue method and angular momentum projection. Here is the continuous network method. We use the continuous network to implement variational calculations and optimize the many-body wave function. And we also use another Hamiltonian generation network to optimize the Hamiltonian used in our work. So we combine these two networks. That is what we call the dual agent coupling method. And this two network has been introduced in detail by Chen Zheng. Okay. After we optimizing the basis, we calculated the energy spectrum for the first 2 plus and the first 2 minus state of boron-12. Then we used the isospin substitution to get the spectrum of the key intermediate states of carbon-12. Our preliminary results are shown in here. And after obtaining the wave functions of carbon-12 and beryllium-8, we calculated the relative motion wave function of the alpha plus beryllium-8. In the right is the traditional theoretical research that mainly focuses on some 0 plus states of carbon-12. You can see for the second and the third 0 plus states, their other wave peak position and the mass radius are so large, showing a loose cluster structure above the 3 alpha threshold. But in contrast, in our calculations of the same channel in the key intermediate states, we can see both the other wave peak positions and the mass radius are much smaller. So it shows a compact structure, which is so different from this states. We also calculated the relative motion wave function of the P plus boron-11 channel. And both these two states also exhibit a compact structure. And we found that in both intermediate states, there is a significant difference in RW peak positions between the alpha plus beryllium-8 and the proton plus boron-11 channels. We can see in this figure, the position is 3.5 FM, but in last figure is 2.5 FM. It means in different channels, the RW peak position is also so different. If the proton is included in alpha cluster, it just means that this intermediate states have 3 alpha cluster structures. Then these two positions should be so similar. So this phenomenon indicates that there may also alpha cluster breaking exist in these two intermediate states, and it may break into the triton plus proton or helium-3 plus neutron. Okay. After obtaining the wave function, we calculated the decay width using the R matrix theory. We choose the channel radius at the position where the asymptotic behavior of the RWA matches that of the Coulomb function as shown in this figure. The gray curve represents our decay width. And combine the partial decay width of many channels and the theoretical formulas, we calculated the S factor of the whole fusion reaction. In this figure, we can see that our calculation for the second peak corresponding to the 2- state of carbon-12, it is consistent with the experimental data on order of magnitude, but there is still some gap between our calculations and the experimental data in the 2 plus state. So in future, we will continue to use our Hamiltonian generation network to optimize our calculations. Yes. And last is my conclusion. Yes. Okay, so thank you for your attention.
Okay. For large questions.
When you show the radii, do you in some way rely on the knowledge of the proton radius?
Sorry, you know. You mean this one?
If you say 2.6, 3.5 Fermi.
Yeah.
Do you rely on the knowledge of the proton radius in this calculation?
Oh, sorry. Here we just consider the mass radius. The proton radius we have not calculated maybe.
No. Yeah, because there are measurements that deviate a little bit for the proton radius, and this may influence this.
Oh, yes. Thank you.
Any other questions? Okay.
You present really parts of AI to according to my understanding. So from your work, how to get the PB fusion reaction cross section?
Oh, you want to know how to get the section? Oh, yes. Actually, after we obtain the decay width, yes, you can see in this page. Here is the formula of the cross section. It is obtained from the decay width of several channels. This is the gamma 1 is the incident, and the gamma A1 plus A2 is the transition channel. The decay rate of two channels, and use this formula, we calculated the cross section.
Also take the alpha spectrum sometimes, right?
Oh, yeah.
Okay. So, thank you.
Okay, thank you.
Okay, now,
Thank you, everyone. The morning session is over. It's time for lunch, and the lunch is still on the first floor. The afternoon session will start at 2 p.m. Please be back on time. Thank you.
The usual explanation for boron is that you have a galaxy mass. Around there condition of the polarized protons and helium-3. Dr. Laswin, are you on the line?
Yes, I'm here.
Yes.
I hope you can hear me.
Flow is yours. Please go
Yes.
ahead.
Okay, let me share my screen. And
Share your screen. Go ahead.
yes, just a second. Wait, I shared the wrong screen. Just 1 second. Oop. And no, sorry, just 1 second. Sharing the screen. Okay. So I hope you can see my screen.
Yes, it's okay.
Yeah. Okay, perfect. Then, yeah, good afternoon or good morning from Germany. As said, my name is Lars Reichwein. Thank you for the kind invitation. I will present our work today on plasma-based acceleration of spin-polarized protons and helium-3. And I hope over the course of the talk I can make clear why this is also relevant to the topic of proton-boron fusion. And our work is a part of a long-standing collaboration of the Research Center in Jülich in Germany and the University of Düsseldorf, but also the Shanghai Institute of Optics and Fine Mechanics in Shanghai. So in the beginning, I want to motivate my presence in this conference. So why do we care about polarized beams for certain applications? And then go over to the updates on the acceleration of polarized helium-3 and also the progress that we have done on polarized proton beams. And finally, I want to give an outlook what are our near future plans. If at any point in time you think I'm too quick with something or want to read up more on this general topic, I would refer you also to our review, which was published end of last year in Reports on Progress in Physics, which covers targetry and polarimetry, but also plasma-based acceleration for all kinds of particle beams, so ranging from electrons to ions and also gamma quanta. So anyone sort of familiar with laser plasma interaction for acceleration of particle beams knows it's already challenging enough to end up with a high quality beam, even if you don't care about spin. So why should spin matter now and why to make our lives even more complicated? Well, as it turns out, spin is rather important for a variety of applications. So for example, deep inelastic scattering would be one topic where high energy polarized beams are needed. So if you want to understand the structure of your proton or neutron, you need a high energy polarized probe beam of electrons so that you can understand the quark-gluon structure better. More recently, also, the group of Yu Chen realized if you have polarized electron beams, for example, and collide them with a laser pulse, you can technically generate a spin-dependent signal if you are looking for axion-like particles. So even for physics beyond the standard model, spin-polarized beams could be interesting. But more relevant to your field here today, and maybe not quite as obvious or well known, is that spin polarization actually has applications in nuclear fusion. So if we have a reaction, let's say deuterium and helium-3, actually if you spin polarize both the reactants, you get an increase in the cross-section by 50%. And this is something that Kulsrud already realized in the 80s. And of course, an increase in 50% for the fusion cross-section makes this rather interesting for our applications. So just here as a detail, this is a nice bit of nuclear physics. You can see here we have the reactions of the helium-3 and the deuterium. And this reaction works also as a proxy for DT fusion because it's just a mirror nuclei. So you see the intermediate nucleus, lithium-5. This has basically exactly at the same energy, an excited state of 3½ plus. And because we go now from 4 available states to 6 available states, we have this increase of 50% in our fusion cross-section. But we're not talking, of course, here at this conference about DT or dHelium-3, but rather proton-boron fusion. And the question is, can we do something similar with proton-boron fusion? And at least in theory, this should be possible. So as you can see here on the left, in 2014, people calculated also that we should expect a similar increase in our fusion cross-section for PB fusion. But the larger question is also, can we somehow even nuclearly polarize our boron? For protons, this is clear how to do, as you will see in a bit. But for boron, it wasn't really that clear. But end of last year in Physical Review C, this group in Cambridge realized or proposed a scheme for polarizing boron nuclei. And they even state here in this yellow marked sentence that this scheme will be useful for proton-boron fusion as it increases the cross-section. Now, I will begin by talking about helium-3 specifically, what we looked at. And from my side, I'm not directly working on fusion, but rather the acceleration of particle beams. So this is the focus of my talk. And polarized helium-3 is the best candidate to look into the acceleration of polarized particles because the sources are readily available. So the polarization of helium-3 is rather state-of-the-art and rather common. You can commercially buy these polarizers. For example, this is a polarizer that is located in Jülich that we use for our experiment, and it uses metastability exchange optical pumping, so MEOP, in order to prepare the samples of polarized gas. With this, you get a rather high degree of polarization, so 75%, and it has a long relaxation time, hundreds of hours, and you can fill these into these spherical vessels, these transport vessels on the right-hand side, where you have 3 bars of your polarized gas if you keep it in a magnetic holding system. In order to accelerate this, we need a laser system. In Jülich, we don't have such a high-power laser system. So instead, we conducted the experiment at GSI Darmstadt, specifically at the Felix laser, which is a petawatt level class laser pulse. It's a bit of an older system, so you don't get too many shots a day, 6 per day. But with this, we were able to do our first proof of principle experiment. There is a side challenge to all of this in the experiment. So Jülich and Darmstadt are roughly 250 kilometers apart. And this means that if we pre-polarize our gas in Jülich, then we need to transport it every morning all the way down to Darmstadt. And for that, you can see in the middle this box where we have our transport vessels, which also uses a magnetic holding field, because once your magnetic field is gone, well, you would lose the polarization. So we use the courier service to transport every morning this gas down to the Felix beamline and then irradiate it. Another side challenge of this experiment is that these transport vessels are at 3 bar, but if you want any kind of useful beam for plasma-based acceleration, you need roughly 30 bar, so 10-fold increase in the pressure. And for that also the experimentalists in Jülich developed then a pressure booster, and the main challenge here is to work with only non-magnetic materials, because you want to prevent any kind of influence on your spin polarization. Putting all of this together, you end up with this kind of setup. In red, you see the Felix laser pulse, and this irradiates this gas jet, which is somewhere in the center of this big bulky setup. And all the surrounding stuff, so the permanent magnets and the coils, are used to maintain the polarization, but we are also able to tune the initial direction with respect to the laser propagation. And then, of course, we need to somehow detect our polarization to see that it is actually preserved for the first time. So in bright green on the side, you can see the polarimeters. And this is important that they are on the side, because we do have a rather long gas jet at sort of low density, 10 to the 19, and a long laser pulse. And this means that we don't really get forward acceleration, but rather a Coulomb explosion at plus minus 90 degrees. So accordingly, we need to place our polarimeters here. And of course, our main interest is to show polarization is preserved during acceleration for the first time, because no one else has done it so far for laser matter interaction. And for that, we need a feasible measurement. So you see the setup again, essentially, Felix beam coming up. The helium jet is coming towards you. And then due to the Coulomb explosion, we accelerate our helium ions to the left and to the right, where we have these polarimeters. And these polarimeters essentially consist of CR39 plates, many of them. And in front, we have deuterated polyethylene foil, so CD2. And what we do is we have the incoming helium ions that can react with deuterium, meaning that we have a small fusion reaction, deuterium-helium-3, which produces an alpha particle and a proton. And since we use polarized helium-3, what we should be able to do is that we measure, in fact, a asymmetry. So between, let's say, the left and the right CR39 plate, we should be able to have to measure a difference in the count of alpha particles that we can detect. And this gives us the analyzing power to then conclude if we have polarization preservation or not. And this is exactly what we see. So in this plot, on the bottom axis, you see the azimuthal scattering angle phi. On the y-axis, you see the asymmetry. And if we follow the magenta line, for example, we see this decreasing trend for one initial spin direction. If now we want to really see that polarization is preserved, it's always good to make a cross-check. So let's say if initially our spins were polarized in plus x direction, well, then it makes sense to swap the initial spin direction, so go from plus x to minus x, and then we should see the inverse trend in our signal. And this is in fact what we see. You see the green line, we see this increasing trend. So it seems that our concept using a pre-polarized target at a petawatt laser works. Yeah? We do indeed preserve the polarization, and we have shown this for the first time. So this was recently published as a letter in High Power Laser Science and Engineering. And this gives us the hope that we could also go to other polarized particle beams. So also protons specifically, which I will cover next, but also, for example, electrons, which are relevant to the other applications that I mentioned. Of course, there's still some optimization to do. As I said, we have this expulsion at plus minus 90 degrees, so this is hardly yet a beam. So in the future, of course, we want to have experiments with forward-directed beams that we can have a bit better statistics. Now, going over to the polarized protons, all the progress so far has been essentially theoretical instead of experimental. And this is due to challenges in the target tree a bit. So most of the targets rely on the photodissociation of so-called hydrogen halides. So for example, HCl, HBr, or HI. And the most commonly investigated in theory is this HCl molecule. And you use these molecules by irradiating them with a UV laser pulse that is circularly polarized. And this leads to, well, the photodissociation, of course, of these molecules, but also we impart the polarization onto our protons. You see, in fact, that this is a much more complicated scheme, and this is due to the fact that these targets can also be used not only for polarized protons, but also for polarized electrons. So why this looks more complicated here is that we use a sequence of dissociation pulses to end up with only polarized electrons in this center channel where we only have these blue particles left. But if you care about a polarized proton target, it's rather more simple in a sense that you use a UV laser pulse for this dissociation and end up with your polarized protons. The only thing you need to consider is that your acceleration process, so the main driving pulse, needs to be timed accordingly, because due to the hyperfine interaction, in fact, what you can see with the sinusoidal wave here is that the polarization is oscillating between the proton component and the electron component. So if you want to end up with polarized proton beams, you need to stage your laser accordingly for driving the acceleration process. Now, already years before we worked more on this targetry side of things, this HCl target had been proposed in a very basic manner, and people looked at mostly magnetic vortex acceleration for this target type. So in this paper by Luling Jin in 2020, they looked at PIC simulations with petawatt class systems, and you see that, of course, if we increase the intensity of our laser pulse, we end up with higher energy proton beams, ranging from 53 MeV to 152. However, also the polarization decreases. So you see in the lowest energy case, we have 82%, and in the highest energy case, we drop to 56%. So not a very low number, but definitely lower than the 82. And depending on the application, of course, you would want to maintain this higher polarization. We could optimize this target. So a bit later, we proposed another setup where we don't use a single pulse, but rather two laser pulses that co-propagate. And this leads to an overlap of fields in the center region. And this is rather beneficial for maintaining the polarization. So this central filament, as you can see on the right-hand side, where we have proton energy versus polarization, in this dual pulse case, we are actually able to improve our polarization from, well, in the worst case, 60% here to about 70%. But of course, it's rather challenging to design an experiment where you have high-intensity laser beams that co-propagate. And if you think about it a bit more, this dual pulse setup could also be seen as a slice in one plane of a Laguerre-Gaussian beam. So we studied also together with Tongpu Yu the option of using these donut beams, so Laguerre-Gaussian modes, and we're able to show, in theory, if you have high-intensity Laguerre-Gaussian modes with an A0 of 20 to 50, your polarization remains on the 90% level, so much, much higher than what we could generate with single or dual pulse cases. But of course, this relies first on the realization of those beams. Now I want to cover a little bit what our plans are for the future. I mean, you saw we did a first experiment successfully with helium-3, which is the first in the world. And of course, we want to build on that and also go to other particle types. So for the helium-3, you saw we have this expulsion at 90 degrees. You see the blue line, mostly mostly transversely directed particle beams and very little as a forward signal for this long gas jet. If we now shorten our target, which is what we can do, so we go from 1 millimeter to 0.5 millimeter, then we see in simulations that we would expect a much more pronounced forward-directed beam. So for the upcoming experiment, we will go to this shorter gas jet and work with that. Another advantage is that we have now a new polarizer. So this was bought by this company Xemet. And the main advantage, you can see it on the bottom here in the left plot, is that this polarizer has wheels, meaning that we can actually bring it down to Darmstadt and conduct the experiment in one go there and don't need this complicated transport process for the polarized helium-3. So this is a nicer, much more compact polarizer that we can use. So this is the update on helium-3. Of course, we still want to go to polarized proton beams experimentally. So rather recently, we re-established our collaboration with the Shanghai Institute of Optics and Fine Mechanics. So this was a bit interrupted due to the COVID pandemic. And beginning of last year, Markus, my supervisor, and I went to Xeom to build up the plans for a coming collaboration on polarized protons, but also polarized electron beams at Xeom. And beginning of this year, we also went there for a month. Markus got designated as a PIFI, so President's International Fellowship Initiative, distinguished researcher from the Chinese Academy of Sciences, and we gave a bunch of talks throughout China. And so in the near future, we aim to build up the necessary target tree, polarimetry, and so on to realize polarized proton beams also experimentally. The advantage is that, of course, with the Xeom, we would have access to high-power laser systems. So pictured down here is the Self 10 petawatt, but of course they also have other laser beamlines we could use. But this gives us the option to do polarized proton beams. And also, as I alluded to in the beginning, with these photodissociation targets based on hydrogen halides, we can also use them to look into polarized electrons, which hasn't been done so far. And this is, I think, a very interesting option to do this at Xeom, and we hope we can realize this soon. So coming to my summary, I hope I could interest you a bit in this topic of spin polarized fusion and showed you that the cross-section can be increased by 50%, which makes this a rather interesting topic, I think, for the fusion community. And it's possible for a variety of reactions, so DT fusion, but also dihelium-3. And specifically interesting for you, of course, also proton-boron fusion. We conducted this first proof of principle experiment, which is published now as a letter in High Power Laser Science. So we saw if we use a petawatt level laser and irradiate a pre-polarized target, we still end up with high energy polarized beams. And of course, we want to go to other particle types. Helium-3 is just the easiest because the polarizers exist very commonly. So we have our future campaigns planned for protons specifically, but also electrons at the Shanghai Institute of Optics and Fine Mechanics. And not led by us, but we are to some extent involved, are plans also looking into polarized DT fusion. So people at the D3D tokamak in the US, led by Bill Heidbrink, you can find a paper here at the bottom. They also plan on looking into polarized fusion, really. And lastly, again, if I was too quick with any details, or you're more interested on the topic, I would refer you to our review paper here. And with that, I'd like to thank for your attention, and I'm open to any questions that you might have. Thank you.
Thank you, Dr. Latoran, for your very clearly nice talk. So now we go to the question and comments. Please.
Thank you for your interesting talk. Tell us, please, did you analyze the problem related to expedience of the use of laser accelerated helium-3 ions for fast ignition DT micro explosions. The idea is that if we bombard the compressed DT fuel with helium-free ions, the hotspot will be heated by both kinetic energy of ions and products of helium-free D reactions. I published this idea several years ago.
Thank you for the comment. We didn't look into this. So for now, we're really focused from our side on the acceleration experiments because this is more our expertise. And we are working, as I said, with the people from the D3D tokamak, for example, looking into the fusion stuff, but this is really led by them, and we focus on the acceleration experiments and theory.
Thank you. And what is your opinion about possibility to accelerate helium-3 or maybe even helium-4 ions using solid targets absorbing helium? Is it possible to irradiate solid targets saturated with helium?
So, if I got the question correctly, so for helium-3 specifically, we are also looking into kind of pellet targets, which is another topic, together with the fusion community. Helium-4 you cannot polarize because it has 2 protons, 2 neutrons, so it ends up with no spin. You can only polarize helium-3. What else was in the question? Sorry, can you repeat the last part of your question?
I understand that helium-4 cannot be polarized, but for some applications, acceleration of helium-4 ions non-polarized can be interesting. And so I asked you about the possibility to irradiate solid targets which absorb some metal, for example, which absorb helium.
Yes, so for solid targets, the problem is if you want to go to polarized beams that...
I don't ask about polarization, non-polarized.
For non-polarized, of course, you can look into foils. I mean, this is rather state of the art, I would say. I don't know specifically for helium, rather less so, but for proton acceleration, this is commonly done with TNSA. Yeah, for us, the challenge is more really on the polarized targets because it's more challenging with the spin. I can say this.
Thank you very much.
Okay. Thank you.
Thank you for the very interesting talk. May I ask if it's very interesting that every day you transfer your helium-3 gas to like 250 kilometers away. And I would like to ask, what's the material that you hold your gas to keep it polarized? And what is the most important thing during this?
So, yeah, I don't have in my head right now too many details. You would need to ask the experimentalists and not the theoretician about this. I just know that it's a magnetic holding setup in this box. There are a couple more details about our helium-3 target. So if you look into our review paper, there is more details on the targetry side also, how this is prepared and transported. So there's a paper by the third author in this list, Chuan Zheng, which looks more into this target, and you would find the detail there. I'm sorry, I don't have an answer on that right now.
Thank you.
Okay.
Oh, I have a question about you're talking helium-3. So you use laser to heat your polarized helium-3 and accelerate those helium-3 ions to collide with a CD2 target. You're talking that acceleration is come from boron exposure, but do you have any spectrum or kinetic spectrum for those heavy ions, those helium-3 ions? I'm wondering, because helium-3 is hard to cool down, to form the cluster or solid cluster. So is it come from Coulomb explosion or acceleration?
Don't think about Coulomb explosion here in a sense that we have any kind of clusters, really. It is a Coulomb explosion in a sense that you draw out the electrons, which leaves you with the ions that then move outward because you have drawn the electrons away. And this is why it's a Coulomb explosion. So the thing
So
is,
you have some liquid helium-3.
I'm sorry?
I'm told, so I guess you are using some helium-3 gas.
Yes, it's a gas, exactly. So in this case, we talk about Coulomb explosion. So we don't have any forward acceleration, or very little, because most of the laser energy is dissipated into the target. And this is why you don't form, let's say, at the back edge, any kind of sheath field, and you will not forward accelerate any ions.
No,
But
yeah.
you still ionize all your helium, draw out the electrons, and then you end up with, well, sort of this channel where the laser filaments inside.
So the strings should be very weak if possible to accelerate those helium-3 ions. But you got about 10 MeV helium-3.
I mean, this is simulation here in this case. So in
Oh,
experiment,
okay.
it would probably be a bit lower, but yeah, essentially, like it's, I think, below 10 MeV what we have in experiment.
Okay.
Okay.
So
Thank you.
the time is okay. So, oh, sorry, one more short one. Yeah, for me, so I think about if we use the polarization, beam technique to the magnetic confinement device. I think maybe the long-term polarization persistence would be important or even essential. If yes, what approach are available to sustain it?
So this is a topic that our colleagues in the US are looking into. So I think the title of this paper at the bottom here is really lifetime of spin polarization in magnetic confinement fusion. So there will be some more details into this. For now, their plans are to use pre-polarized pellets and inject them, but they will need to see. So there's only very sparse research so far, I would say, on polarized fusion. There are, like over the couple last years, some papers that look into how well polarization is preserved in fusion-based setups. Yeah, but I think this will be something to figure out in the near-term future when we actually can do something about it. For now, it's more a targetry and acceleration-based study for us.
Oh, okay. Thank you very much. Thank you, speaker again. Okay. Thank you. So next speaker is Professor Lu Jianling, come from Peking University. Welcome.
Okay. Thanks the organizer for giving me this opportunity to show our recent work. This is the first time for me to be here. The title is Study of Carbon 12 Resonance Relevant to Fusion with LACPA and ATTPC in Inverse Kinematics. LACPA is a large accepted charged the charged particle detector developed at Peking University. ATTPC is active target time projection chamber. Inverse kinematics is shown here. In our experiment, protons are target. And the heavy particles such as boron11 is beams. I'm Jianling Lou from Peking University. The data of our experiment is very complicated, so it was analyzed by my PhD students. Four parts will be showing in this talk. First of all, let's show the motivation. Sorry. Okay. 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 Let's first of all let's see the motivation. We all know that this reaction is a clean energy pathway. However, the reaction mechanism remains controversial. Someone believes that this reaction through a compound nuclear to form the resonance in carbon-12 and then decay to 3 alphas. But the others argue that the direct Triton cluster transfer reaction dominates. And this one is the most acceptable one. This is the fusion cross section as a center of mass energy, and the maximum cross section is at the center of mass energy of 620 keV. If the compound nuclear assumption is right, this peak corresponds to the resonance at 6.58 MeV in carbon-12. Nearby, the 60.11 and 7. And the rule angle really angle energy. Right? As a that in the we can see the 6.11 resonance, but there is no 6.58 MeV resonance. Then we reduce some alpha particles with lower energy, and the spectrum seems more clearly. And we see that the 2+ state is more normal than the previous one. We also see that for the 6.11 MeV resonance, it predominantly decay to the 2+ state in beryllium-8 and little to the ground state of beryllium-8. Furthermore, by choosing two alpha particles penetrate the SSDs and one low energy particles stopping the SSDs, we get the more clearly spectrum. We see that the 6.11 resonance is more clearly, but the width is too large. Maybe it mixed with other resonance, and we can see here clearly this resonance mainly predominantly decay to the 2+ states of beryllium-8. But there is still no 6.58 MeV resonance. We also use the Proton and Boron11 tool for the coincident event to reconstruct the resonance in carbon 12. This is the spectrum. We see that the 6.11 resonance is still very clearly, but the 6.58 resonance is little some hints. So there is a short discussion why in our experience nearly no 6.58 MeV states. One possible explanation is that in our experiment, the reaction mechanism is very complex, such as the two neutron knockout from carbon 14 or the inelastic scattering of carbon 12 can populate carbon 12 resonance. This leads to the alpha origins ambitious. That means we didn't know where is the alpha come from. So as a result, we can explain our beryllium-8 spectrum of various ghost state and strange 2+ state, and also a large background in the carbon 12 spectrum. Another possible reason is that for those two resonance, 6.11 MeV and 6.58 MeV, they have different spin parities. So the maximum excitation cross section of those two states should be at different angles. And this phenomenon is similar to the reference. And we also try use our data, full-field data, to search for those resonance. We saw that if we use the 3 alpha in coincident with Triton, we can see those 3 resonance clearly. Despite the statistic is limited, but we can see that for this the resonance is wider than the nearby one. This is reasonable. As our estimation, the width, the intrinsic width of this resonance is about 300 keV. It seems reasonable. So we performed another experiment to further investigate this question. And the second experiment of LACPA is carried out at the Institute of Modern Physics. And beams of oxygen 14, nitrogen 17, and carbon 12 are used. We can use the one proton knockout of nitrogen 17 and inelastic scattering of carbon 12 to populate the resonance. We use the digital DQ to record the data from T0 and the controversial DQ to record the data from other telescopes. In order to for kinematics measurement, we updated our experiment, especially the telescope T0. First of all, we increase the number of DSSD from 3 to 4 and expand the system iodide detector area from 2 multiplied 2 to 6 multiplied 6. And in order to reduce the detection threshold, we change the readout of all the system iodide detectors from PD to APD. This is the PID performance from this experiment. And PID performance is improved significantly. And the charged particles up to z is equal to 8 can be clearly identified. And the detection threshold is decreased. We can choose protons very clearly from other particles. We also record the pulse shape of silicon detector and system iodide detectors. We can see that using this two-dimension spectrum, we can discriminate low energy protons from the background. We also record the fast and slow components of system iodide detector. And we compared the short to long integration method to the rise time method. We found that the short long integration integration method can obtain a better figure of merit for z is equal to 1 and z is equal to 2 particles. That means this method have a good PID. So after all those improvement, we reconstruct the invariance mass spectrum of beryllium-8. The result is here. We see that the energy resolution of the ground state of beryllium-8 is up to 15 keV. This resolution is better than the previous one. We also see that there is no ghost peak. That means all the alphas are mainly from the decay of beryllium-8.
And then the data analysis is going on. Hope we can focus on the controversial issues about the resonance in carbon-12 relevant to the fusion reaction. Because the experiment has just finished 1 month ago, so the data is on here. We hope next meeting we can give more results. And next one is the prospect and the summary. For those 2 experiments, we measured the resonance in carbon-12 indirect. So next one, we hope to measure this fusion reaction directly using the LACPA and the ADTPC. Our experiment should firstly perform the in-inverse kinematics. I mean the Boron11 is beam and protons are targets. The physics goals of this experiment is to study the cluster structures in Boron11 and carbon-12, and also measure the hydrogen-boron fusion reaction with full kinematics. Note that the Boron11 beam with 100 hours has been approved by the CIAE, and we hope to use the ATTPC instead of solid proton target due to its advantages. For example, it has nearly 4 pi solid angle. Its detection threshold is very low. It's not affected by the target. And we have the ATTPC prototype. This is the photo. And we also developed a lot of other detectors. For example, at 0 degree, we plan to use the GGG detector array. Those are the test results for the GGG array. For the 600 and 62 keV gamma rays, and the energy resolution is up to 10%. And for the alpha particles, and the energy resolution is up to 6%. Those are the test results for the cisma-iodide detector. We can see that for this wedge-shaped one, for alpha particle, and the average energy resolution is up to 6%. And for this square one, for alpha particles, the average energy resolution is up to 4%. So this is a short summary. Our investigation is focused on the excitation energy, intrinsic width, and decay modes, and the decay branch ratio of carbon-12 resonance. Those resonance is relevant to the hydrogen-boron fusion. Focus on those questions, we performed 2 experiments of LACPA. In the first experiment, we found little evidence for the 6.58 MeV evidence. And we also found the decay branch ratio and the intrinsic width of 6.11 MeV resonance is not reasonable, so need more investigation. And we also we just finished the second experiment of LACPA. In this experiment, we do a lot of improvement. Now we only get the invariant mass spectrum of beryllium-8. For its ground state, the energy resolution is up to 15 keV, very better than the previous one. And hope in next year we can get the threefold or fourfold coincident events to reconstruct the carbon-12 resonance, and hope to report them in the next meeting. And in the future, we try to perform the direct measurement of this fusion reaction with full kinematics. That's all. Thanks for all my collaborators. Thanks for your listening.
Okay.
That's all. Thank you.
Thank you. Comment.
Yes, I'm trying to understand the basic debate here between the direct nuclear reaction and the resonance state. Is it basically the amount of time that the reaction takes, that in the resonant case, the resonance state exists for, I gather, something like 10 to the minus 19 seconds, but in the direct, the reaction is much faster and the alpha particle does not remain together with the beryllium for that long, but the reaction takes shorter. It's just like two billiard balls coming together. And
so what's your main question? Your main question is it's not useful to detect this reaction.
I'm trying to understand what the physical process, what the difference in the physical process is between the hypothesis of the direct nuclear reaction and the hypothesis that we're all more familiar with forming an excited resonance state of carbon-12 then falls apart. What's the difference in the physical process? Does one take less time than the other?
Detect one time? What's your meaning? Detect one time?
I'm saying, is one process faster than the other? Does the direct reaction imply that the nuclear particles are together for a shorter time than the resonant?
Yes. Yes, I agree with you. The direct reaction is a faster reaction. It's a very fast reaction. But I want to clarify the reaction mechanism of fusion reaction, because someone said it should through the compound nuclear to form the resonance in carbon-12. If this picture is right, we should observe those resonance in other reactions such as a direct reactor. So that's my that's why I want to investigate it. I know that the fusion reaction and the direct reaction are very different. Direct reaction is very fast and just in the face of the nucleus. Okay.
Thank you very much.
Thank you.
Very nice talk. Another word. If I got you. Maybe you say you have two different chairs for the state. you try to figure out if you got two minus state, but if one of them you cannot repeat the 2 plus state. I'm wondering why you got one is DT, another maybe
DT.
One is DT.
Yes, this is.
Yeah, here you got 16.11.
Yes.
But in this is come from DT.
Yes.
Yeah. And another channel, but you cannot figure out and find out this excited state. I'm wondering how is because the resolution of your silicon detector, or because basically physics you cannot show up here.
Okay. In my opinion, it's depend on the reaction cross section. Not due to the resolution of our silicon detector. For example, this reaction is one neutron transfer reaction. Its differential cross section or angular distribution are very different to the inelastic scattering data or the two neutron knockout reaction. Maybe just at these angles. This
you happen to find.
Yes.
Do you have so you construct the excitation element using infrared mass spectrum?
Yes. For this spectrum, we reconstructed it from 3 alpha in coincidence with Triton. The Triton is measured by the telescope TAF. That means the large angle telescope.
Yeah, this good. So, do you have any Dallas Pro? Maybe it can help you to find them out.
Yes, you are right. That is plot is done by my PhD students, but I don't show here now. Okay,
thank you.
Second.
So, last question.
Well, actually, I'm not doing. I just want to make a comment.
Okay, thank you.
About the reactor, our undepressed mechanism. To my understanding, is low energy and light nucleon. It's still direct nuclear reaction, even if it's at very low energy. The main reason is that in these cases, the open channels are very small, so they don't have much complication. So then, to my understanding, compound nuclear reaction is infinite number of direct nuclear reactions. So you have so many nuclear direct processes you cannot do individually. Then you make statistics. But if the open channel is very small, for example, here we have only 2, that's a scattering and transfer. Then it should be described by scattering theory. Then this is direct nuclear reaction. This is my understanding. So it's different picture from heavy ion nuclear reactions, because heavy ion nuclear reactions will have many states in the high status in energies. But for these large ones, we have very few states. So we have very few open reaction channels. Then we can describe it using direct nuclear reaction.
Okay, so let's start the speaker again. I'm going to the next speaker, Professor Ma Xing comes from the Beijing University. His topic is hydrogen boron reaction in the nano structure or targets under the radiation of head or laser. 也就可以，那这个是吧？
这是计划。
Good afternoon. Sorry, I changed my title a little bit because I realized that my previous presentation probably cannot fit 30 minutes talk. So I changed a little bit. But it's more, I think it's more relevant to this topic of this forum, right? I call it nanofield fusion, promise of pipe dream. This is, I think, an interesting topic. Because I just before the talk, I really did some work to dig more interesting stories, and I will happy to share that with you. Okay, so I just use AI to draw in a figure. It's a fusion energy. This is just a few minutes ago before I gave the presentation. In this figure, I show that what my understanding about the fusion energy, what it can bring us in the future. As we know, it can bring us to help us to do the deep space exploration and may give us unlimited stable power and can help us to live in extreme environment and also maybe probably can give us autonomous discovery. That means AI. This is, all of them actually are still far away from our current life. So it's more or less like something in fiction, but in our we call it dream. Recently I realized that this is exactly what the fusion energy matters. Because many people said the solar cell, they can already provide sufficient energy nowadays. Why do we need fusion energy? I would say because it can give us dreams, can bring us dreams, give us a chance to live in a world which only in our dream. This is, I think, worth to do it. Okay, anyway, back to the science. So this figure shows that the investment in fusion energy company in the last 5 years. As we can see, it rises sharply after since 2025. And now, for example, in 2025, in each year, we get $4 billion investment. This is a very quite fast rising. And as we can see, the major players are the US and China, probably, and Germany. And this is, I think, a good signature for us, to see, okay, this field is becoming hotter and hotter and more money coming. This is a good thing. And also, if we look into more, and this figure shows that how much investment in laser-driven initial fusion energy company. This is what the main topic I would talk today. I will focus on the laser-driven initial fusion. And for that, we can see more or less the same. It starts right after 2022. And some companies get some investment about 50 million level or 100 million level. And more in the last year, we have some companies get 200 or even 400 million every time. So we can see it rises very quickly as well. Although compared to the magnetic confined fusion, it probably 1 order or half order small magnitude lower, but still it's quite a lot. Oh, but I don't know what happened. Okay. Anyway, the topic I want to talk today is about a company called Marvel Fusion. Marvel Fusion is a company built in Germany and co-founded by two professors. And they received their first investment in 2019. And in the last year, they got like 400 million for the Series B plus. So, and as we can see, among all the companies, they are getting relatively speaking a lot of money.
Europe is not.
Europe. So it's quite a lot actually.
So now let's look at the schemes all the companies are working on. Basically, first of all, we know that there are indirect ICF, right? Because this is the only scheme that has demonstrate the G larger than 1. And in this scheme, the laser irradiates some Hollery, and the X-rays comprise the capsule and compress them to a very dense and hot spot. And parallelly, actually, more companies are seeking the possibility to direct ICF because they are more economically. Theoretically, the energy needed for this fusion is 1 order magnitude lower compared to that. So in the future, power plant, probably this is more promising in some people say that. And for the Marvel Fusion company, actually, it's quite interesting. They use a very novel but controversial scheme. It's called I call the nanofuel fusion, which was proposed. This is the only company, only one company now are pursuing this way. And it is some hybrid. They use hybrid fuel and without compression. But right now it's very controversial. Is it possible or not? This scheme. So what raised my interest is what kind of idea can grow a billion-class company in 5 years, and what's the physical foundation of this pathway? Is it sound in physics? I think it's interesting, maybe interesting for you too. And how did this country come about? What's the history of the debate? I will share that with you today. Okay, here is our start. In 2022, actually, Professor Hartmut Rue and George Kohn, they are the co-founder of this Marine Fusion company. They published a serious paper in 2 years in Archive. This full paper basically is the main foundation of their scheme. If you are interested, you can download the paper and read them. Basically, what they propose, the most important claim is that so G over 1 is possible in an uncompressed, near solid density nanofuel target. This is quite different from this ICF scheme as we saw, because in all of the, no matter it's either in indirect or direct, eventually you need to compress the fuel into 1,000 time of solid density. But in this case, it doesn't need to compress the fuel, only solid density is okay. And so it releases the need for engineer release quite a lot. You don't need to face about the instability problem and so on. This is what they claim. And the major plan that they, instead of use a solid target or gas target, they use a nanostructured DT plus PB compound target. By using such target, you can irradiate by femtosecond ultra-intense laser. They can highly efficiently produce MEV level non-thermal fuel ions instantly almost. And because of this instant produced, and the fusion reactivity can be significantly enhanced compared to normal DT target because of some other additional reasons, such as self-generated B field and high stopping power and this microscale pitching cardiac structure. This is what they claim unique in this structure. So is it true or are they valid, this foundation? Actually, for the first one, can nanowire target produce high energy density matter as claimed? I would say probably yes. In this field, actually, there are already many publications. This is not all of them. I just list some very important one. And here is a review in Optica 2022-24. If you are interested, can look into it. And also,
I want to point out here that actually in CAEP in 2010, they already published 3 papers, theoretical paper. This is actually B front. It's very important paper from Raukas group. Okay, so the physics is like this. In such a target, you have a nanometer scale diameter wires, and the laser irradiate them parallelly. And the electrons under irradiation will be pulled out into the gap between the nanowires. And subsequently, the ions will be accelerated in such shear field and gain energy to several hundred keV or MeV level. And these ions will be stopped in nearby nanowires, and also the return current in the wires also hit the core of the nanowires. These 2 effects will help you to get something like a temperature of 300 eV, 300 keV, or even higher, with only a Joule level class laser. This is some work we did several years ago. Those, let's make a comparison between this ICF hotspot and such new form of high energy matter. As we can see, in the former case, they have a diameter roughly tens of or to 100 micrometer, and the volume is about 2 orders of magnitude more. But of course, the driving power is also much higher. It's like 5 orders magnitude higher. So it's very naturally that the total energy is more. And the biggest difference is that the density, as we can see in that case, it's about 1,000 solid density, and in this case, it's only 1 below or near the solid density. About the temperature, in the latter case, it can be higher. And if we calculate the energy density in this case, actually, it's similar, actually comparable to this hot spot. It's 10 to 9 or even higher maybe. And in this case, it's 10 to 10 joule per cc. So if we only look at this, this scheme is quite attractive, right? And but actually, this very hot and tiny high energy density per plasma, they will evolve. They will expand and cool down, right? And the time scale is about femtosecond to picosecond. Let's say 1 picosecond. And within that time scale, the temperature will drop to keV level. And at this temperature, probably it's relevant to the DT fusion, right? This is what we need for such temperature. And after that, it further cools down and irradiate. This is maybe not interesting for us. And if we calculate this process with the temperature that's above this fusion temperature, we can see that the N tau is about 10 to 16. But we know the ignition for TD fusion is 10 to 19 at least. So it's 3 orders magnitude lower. That means if we only use such structure, anyhow you cannot ignite. This is a very simple conclusion, because basically the time is too short and the density is not high enough, energy density is not high enough. But why they claim it works, and we can give a revisit to Rose and Cohn's scheme. Actually, they propose a very smart idea that they call it the compound structure. Basically, it's a cylinder-like target with a radius of 1 or 2 millimeter. And there are many nanowire arrays, and between them, they fit the field with DT field. And on the outer side, there is a gold ball, which is used to reflect the radiation. So
to keep the radiation energy inside this reactor. Okay, according to their calculation, that if you use the driving power related to energy of 4 millijoule, it's possible that you can achieve a temperature of 5 to 30 keV and in confinement time of about 3 to 8 nanoseconds instead of picosecond. Okay, this is very important because if you have nanosecond confinement time, this n tau is probably close possible. And eventually they calculate that the Q could be to 2. Of course, not so high, right? But still, it's larger than 1. And so basically, if we think about it, actually the system, why it works, because this is a very large system, large enough. The rho r is about 0.4 gram per square centimeter. And because they are large enough for ion confinement and alpha particle stopping. So literally, it's a non-compression fast ignition fusion scheme for a very big system. After their proposal, actually, very interestingly, Lechner, who immediately published a series of comments about their idea, because their claim is very contradictory to our old understanding, right? Because it claims that you don't need to compress. And he proposed at least 5 pieces of comments, and the Rowe and Kahn replied 2 of them in 2 years. What's the main point of the criticism? I would summarize as below. In Lechner's idea, that the Rowe's opinion that all the fusion energy were deposited to the ions, the alpha particle, this is actually invalid in his opinion, because Lechner thought that 95% energy will deposit on electrons instead of on ions. This is very different from what they claim. And the Rowe, they replied recently that, okay, you get this conclusion simply because you didn't, the formula you used is wrong. It comes from a very light material. But we are using the heavier material and mixture. This is different. And the second criterion is that the Lechner said that, okay, you underestimate the Bremsstrahlung loss. Actually, the Bremsstrahlung energy he calculated is 50 times higher than they calculated. So this is a quite big difference. And about this, I think they can argue that because we have a gold ball, which can, work as a black, so black chamber. So that in that case, the energy will not be really escaped. And also because in terms of the need of fuel pre-compression, this very core at this argument that the Lechner said that it's indispensable because of there's 2 mistakes they made. So this is it will not work. And of course, there's another disagreement about radiation temperature equilibrium. And Lechner said you will never get equilibrium in this case. And so this is some other matters. But basically, he disagreed about many things, about the stopping and the radiation balance and so on. Oh, so what's the current status about Marie fusion? And in spite of this, I would say, comment, the company actually, they are getting very well.
and they continuously getting money. And in last year, actually they got 400 million euro, and they are building a laser system called Atlas in US. And it was 3 synchronized petawatt laser, in total 7 petawatt peak power, and it will be commission will be in the end of this year or in next year. That's a plan. And they also making a plan with this Siemens Energy. They said, okay, in the future we will build a 100 milliwatt power plant based on this this idea, nanofuel fast ignition idea. Okay, this is what I learned from the website. I didn't, you know, to talk to Hartmut recently to confirm that. But anyway, as we can see, the impact factor of this paper is really, it's not measured in citation time. It's measured in hundreds of millions of euros. This is what I would say. Okay. So make a summary. It's settled that the irradiating nano target indeed can produce a high efficiently produced laser ion coupling. This has already been proved in many experiments, I would say. And also, but this dispute is still there. Does it lead to uncompressed fusion energy? This is very unclear. And so what's next? In my opinion, actually, what we are now is we know nanowire heating is very efficient, but nanowire fusion actually there are quite a lot physical problems we are not fully understand, I would say. For example, about the stopping and how evolve such far away from equilibrium and non-uniform plasma will evolve, and how important the pinch effect is. This has Professor Zhang said, and the energy transfer and the balance, and how to further increase the yield. This is actually, I think, worth to be explored right now. Of course, in the future, maybe we can go to ask whether nanofuel ignition is possible. This is in my opinion. Okay, I don't have so much time, but I will give a quick introduction to our recent work. Right, as we know, this nanowire fusion experimental result. This is the most important result. It was published in about 10 years ago, 12 years ago. They generate they measured the DT neutron, a DD neutron with a yield of 10 to 6 by using 1 or 2 joule femtosecond driving laser. This is a Rokas group's work. And after that, there are also many other works. I don't want to go to details. And this figure summarizes that, okay, now what we are, as we can see, in spite of this effort to further increase the laser energy, the yield, if we normalize to per steradian per joule, actually, they don't increase quite a lot. This is somehow out of the expectation, because Zoka in that paper, they claim that it will, you know, rise nonlinearly, but it's not. This is the current status for the DD fusion. And there's also one only single work done by Professor Zhang's team. This is a PB fusion, PB nanowire fusion. They published last year, and they got a yield about between 10 to 6 or 10 to 7. This is the current status of this nanowire fusion. This is just a short review. What we do, actually, we do the same thing. We use our petawatt laser to shoot a target. It's very similar to others what I do, and we use a CR39 to measure the alpha particle generated in the experiment. And we should do different target, the planar BN target and the B-doped CH nanowire target. And this is the result for planar target. This is a cumulative two-shot result, as we can see, right? This small dot, they are protons, and this big dot, they are alpha particles. And we can easily calculate them and divide it by the solid angle. And we can get a yield about 10 to 8, 10 to 6 per joule per steradian. This is from a planar target. I think it's reasonable, this value, somehow, consistent with our result, maybe a little bit higher, but still reasonable. And what surprised us that when we shoot the nanowire target, this is the result. The same distance, the same CR39, and same etching time. We see all is fully saturated. And this is the planar target, right? Okay. So to make a very clear measurement, we further train this filter from 10 micrometer to 20 micrometer. This actually changed a lot, we will see later. And even with the 20 micrometer aluminum foil, we see a lot of R particles. So this is a very clear evidence that the yield is much higher. And we further calculate for this one, although it's quite saturated, we can give estimate the lower limit to not taking into account the overlapping, right? And we can get a yield of about 6 times 10 to 8 per joule per steradian. This is easy to check, right? Because we just count the numbers and divide it by the solid angles they have. This is a two-shot, accumulated two-shot. And for the 20 micrometer, they look less. The number looks smaller because this 20 micrometer aluminum foil, actually, most of the upper particles, they have an average energy about 4 MeV.
When this question, let's move on to the post-flash talk. Okay.
Now the we now have three speakers. First is Jian Zhang.
到第三个，
这个是吧？
对，是这个吗？
是我的狗。Good afternoon, everyone. My post title is the exploration of green streamline energy conversion technologies in PV fusion. PV fusion is different with the DT fusion. The green streamline and energy loss is bigger than the fusion power itself. So now we are studying ways to recover this large radiation. We did a calculation for beam streamline power and energy spectrum. We found the main energy range to recover is around 100 kV. And we put forward two possible recovery methods. The first one is convert radiation into heat and then turn heat into electricity. This is similar to thermal power plants. The second one is directly turn radiation into electricity using semiconductor. We are now checking whether this method can work. Our research is still at early stage, and there are many problems we have not yet considered. So we're looking forward to exchange ideas on this topic and welcome suggestions and new method. Thank you.
Next speaker is Huang.
Hello everyone. My name is Huang Hairong. I'm from EN Fusion. Firstly, introduce the background. Traditional heating method heat electron first, and they transfer energy to fuel ions through collision. This process takes massive radiation energy loss and reduce fuel ion heating efficiency. So we research a method with collisionless. The method use ion Bernstein wave to bypass collision. The wave is driven by by a positive velocity and velocity gradient distribution beam. The simulation use epoch code. The simulation results show that the beam transfer energy to electron and background proton, not to boron, and greater to thermal proton. And we also try we also try an active counter method to enhance great enhance proton hitching effect effect always theta wave is added in the simulation. Its energy density is 0.35% of the initial beam. The simulation results show the background proton energy transfer almost doubles, and electron don't last more. Thank you for listening.
到这儿就念过。
Okay, hello. Good afternoon, everyone. I'm Jian Guochen from Fusion Group, ENN Fusion, and my poster titled "The Practical Exploration of AI on XR50U." We believe that AI should not only be used as a prediction tool, but also an integrated scientific capability that combines physics models, engineering knowledge, and autonomous decision making to solve the difficult problems in design optimization, plasma control, diagnostic, and scientific discovery. So we first developed a framework combines 3 different timescales, integrates large language model for planning and surrogate model and AI speeding up technology to digital twins. And then we finally deployed the model for real-time control to make the plasma stable and more safety to assume high performance and parameters. So left-hand side is the framework and right-hand side is the some practical result. The first one is the stable plasma operation. We have more than 160 dedicated experiments with the RLN model prediction controller. And also the plasma current is almost operated in 500 kiloampere level with the control duration up to 650 milliseconds. Also included the multi-objective and tragedy capability. And the disruption also is important. Right now, we achieved around 82% true TPR and 16.5 APR, but still a long way to go to make the operation more safe. And also, the MGI experiment confirmed that we have need at least 15 milliseconds in advance for the prediction. And real-time technology also were used for plasma real-time equivalent reconstruction. Also, we have achieved using the pure GPU accelerated solver, which satisfies the real-time control. And also, we are using the large language model, including large vision model for the NBI tuning, just using the prompt engineering. And we developed a Fusion Evolve framework for based on the large language model for fusion design, optimization, and control, which achieved more than 100 times speed up for the MPC controller algorithm. And also, we developed a fusion data foundation to support the AI-enabled R&D paradigm for the fusion. So we hope this practical exploration demonstrated how AI can accelerate the fusion research and inspire the closer cooperation between the AI and fusion communities. So thank you, and we're looking forward to discussing our work during the poster session. Thanks.
Thanks for all the speakers. Okay, we will have a coffee break now, and please come back after. Thank you.
下个两个都是在线的，
头两个都是在线的，然后对，只是他们就在线上。
在线上。
对，然后他们现在不是还没上呢吧？
还没上。
先吧，他是这个是吧？对。
叶博来给了吗？他就在后面。
给了。
那也行。
切了。
Exactly what we're talking about. And the game doesn't get faster. Yeah, yeah, just fire.
Good afternoon, everyone. My name is Yue Jiangshi. I will chair the second session in this afternoon. In the next session, this session we have four oral talk. The first speaker is Dr. Zegar Stanker from UKAEA. His title is Integrated Modeling of Reactions in Energetic Particles and Metal Were Imputed in Tokamak Plasma. Let's welcome Zegar's talk. Yeah.
Thank you very much. Good morning. Can you hear me well?
Yeah.
Yes, perfect. Okay, good. Then I'll commence. Right. Good morning, everybody from the UK. I'm sorry I could not join you in person. I would like to thank the organizers for inviting me and still allowing me to give this presentation remotely. So I'm Giga Stanzer from UKAEA. I'm the Plasma Core Team lead. And I will be talking, as the chair kindly said, about the reactions between fast particles and metal wall impurities in tokamak plasmas. Now, before I commence, I just want to acknowledge the numerous authors that have contributed to this, without whom this would not have been possible. So it was a big international collaboration. And a special thanks goes to the Uppsala University and Josef Stefan Institute colleagues. So, for the motivation, the core of this talk will talk about our study of the fusion between fast ions and plasma impurities. So first of all, why are we interested in this from the tokamak perspective? Well, these interactions offer a source of fast ions, which we'd like to study, such as DT-like energy alphas, fast hydrogen isotopes, and low Z fusion products. They can be used as a fast ion diagnostic. Mainly within these reactions, we release signature unconfined products, such as neutrons and gammas that can be detected and then infer back on the properties of the fast ions. They can also produce a radiation source. Now, this can, of course, be seen as a safety issue, especially if this happens in what we believe are aneutronic, let's say, commissioning plasmas of early phases of tokamak operation. But if you flip the story, basically, this can also be an early fusion source if you know how to trigger it and control it, and can be used for diagnostics, calibration, and commissioning. So plethora of applications. Now, this particular work that I'm talking about here was started as part of the Eurofusion work package preparation for ITER operation in 2022 to address the proton beryllium radiation source, which was then still expected in ITER's pre-fusion power operation phase, namely in helium plasmas, where MeV range protons were expected to fuse with intrinsically present beryllium impurities. So what we've proposed at that point is to actually take these predictions for ITER and actually run experiments on JET and then integrated model it and try to see whether we can validate first the experimental observations and our integrated modeling. So the most of today's talk will be about proton beryllium the fusion chain. Now, this is a two-stage reaction chain that produces charged and neutral fusion products. Now, let me lead you through the various reactions that are relevant here. So the primary reactions, here shown on the left-hand side of the graph, can be split into two categories. The first one, the one that is the dominant neutron emitter. So again, this is between fast protons and beryllium that produce directly a neutron and a boron. The interesting bit about this reaction is that it is endothermic, meaning the Q is negative, which means we need to supply net kinetic energy to actually trigger this reaction with a really high energy threshold. So the cross-section for this reaction is shown here on the lower left-hand side graph with the red curve. You can see a 2 MeV threshold, so really needing a highly energetic population of fast protons even to be able to trigger this reaction. Whereas the other two primary reactions produce confined charged particles. They're exothermic as per the usual. And why this is important is because these alphas and deuterons that are produced here are then slowed down in the plasma and then themselves drive and trigger the secondary set of interactions on beryllium, which is between fast deuterons and alphas and the beryllium impurities, releasing neutrons, gammas, and other charged products. Now, from the cross-section perspective, the only thing I'd like to emphasize is that these are reactions with non-negligible cross-section levels, similarly to the Proton11 boron, and they top off just underneath 1 bar. So let's say highly probable reactions. So what we set off as our first objective is to basically run dedicated experiments in the JET device in helium and deuterium plasmas, and basically develop a scenario in which the proton-beryllium fusion would be the dominant fusion driver. Obviously, helium is a natural choice for this because it's in principle aneutronic. So we started off our development in helium. I used 4 main actuators, basically. So this is the RF power on H minority, the plasma fueling, H buffing, and B field. All of this to do what? To basically decrease collisionality and increase the RF power density on the HRF minority to basically create a highly energetic population of fast protons, which would then trigger fusion on the intrinsically present beryllium due to JET's beryllium tungsten metal wall. And we've succeeded in this. So what I show here on the right-hand side is basically the summary of the neutron yields recorded in the whole of the JET 2022 helium campaign, where the x-axis is simply the pulse number, and the y-axis here is the integral neutron yield. Now, the red dashed line denotes the average neutron rate at around 2 × 10⁻¹1 neutrons, whereas our discharges are here denoted in the stars. So you can see that we've managed to, by tailoring this proton-beryllium fusion, achieve a neutron yield which is 3 orders of magnitude higher than the background of these helium plasmas. Now, obviously, helium is aneutronic, so all of the neutrons that we see in this average emission, in any case, are stemming from the fact that we have deuterium retained in the wall, or even tritium, that contribute to this background emission. Although, as you know, helium fusion does not emit neutrons. So we've successfully basically achieved the highest interneutron yield in what is deemed an aneutronic plasma. So to lead you through how these pulses actually look like, so there were steady state conditions pulses at 1.45 megaamps and 2.8 Tesla. So this is panel A here on top, with an extremely low core density of around 1.5 × 10⁻¹9 per cubic meter. So again, that low collisionality that we're after. And we had around 5 megawatts of stable RF power tuned to the fundamental resonance on the H minority at 5 megawatts. We've managed to achieve high core TE of around 8 keV on axis, which obviously again helps us with the collisionality, whereas TI, as is expected, is 2 keV, so it's barely driven by anything except for the equipartition. We've had a high Z effective of around 5.5, again due to the intrinsically present metal wall impurities and low density. The hydrogen concentration was well controlled at around 2.5%, shown in panel K here. which obviously is more or less around the optimal value we have in JET for HRF minority power density. And then importantly on panel M, which is the lowest of here at the bottom, we basically show the neutron yield that we have achieved. Now the red and the blue curve show our two trophy shots. These are 11184, 11185, both of them at a stable neutron rate at around 5 to 6 times 10 to the 13 per second. What we show additionally is this comparison against the previous attempt to trigger proton beryllium fusion, pulse 91667, which is published in Krasilnikov's nuclear fusion paper. So we can see that we've sort of achieved higher neutron yields, higher fusion yields, and most importantly, these were steady state. After this was done, we've also ran some deuterium discharges as twins because we needed some additional diagnostics input. And after having that, we've basically looked into the proof that we had that what we had driven was indeed proton beryllium fusion, right, which is important. We had several neutron and nuclear diagnostics looking at our plasma, among others, Faustein loss detector, the neutral particle analyzer. We had spectrograms for basically Faustein-driven nodes, and we had nuclear detectors such as fission chambers, and among others as well, gamma spectrometer. So in the sake of time, I'm only showing the gamma spectra measurements here, which I believe is a unique measurement of this experiment. Again, with all of these, fast particles interacting with metal water impurities, we have signature fusion products emitted, including the gammas. What you see here is basically the measurement of a extremely dominant and prominent gamma peak emitted at 3.56 MeV, which is the result of the primary interaction between fast protons and beryllium that emits alphas, lithium, and among others as well, this gamma peak. What we show with the other lines is potentially the other candidates that could have presented a neutron and gamma source that would have been parasitic in our case, such as the interactions between really fast beryllium, really fast deuterons and alpha and beryllium. But as you can see here, these are negligible or non-existent. And this is really, let's say, one of the major proofs that we had that our fusion proton beryllium was the dominant case, which of course is then supported by the integrated modeling, which I'm going to talk for the rest of my talk. So what we have done then is we've modeled this two-stage fusion chain with a framework of integrated modeling that we've developed, which is all based on JET plasma diagnostics input, which we input into the transcode using NuBeam, Toric, and FPP to calculate the RF accelerated proton fast time distribution function. And also couple this to predictive JETO using Sanko, mostly to derive the plasma composition, most importantly, the impurity density profiles, namely beryllium. The fast proton distribution function is then fed into locus GPU, which is an orbit tracking code that corrects that distribution function, improves it for prompt losses and finite alarm radii effect. Then we feed that into DRESS, which is the kinematics code that enabled us to compute the fusion product source profiles and energy spectra of the fusion products flying out of these reactions. And obviously, we again have a two-stage chain. So first of all, we could calculate the sources of the primary reactions, and then we take the sources of deuterons and alphas created in the primary reactions, and we feed them back into locus to basically orbit track, slow them down, and loop this back into DRESS to then calculate the sources of the secondary reactions. Also pasting on top any sort of residual fusion products that we have from what we call parasitic fusion reactions in this case. So DD, DT, and TT, as we said, because of residual isotopes that were still there. Now, I'm only going to show a couple of results here, sake of time. So I'm showing here the primary, the results of the primary analysis of the fusion between fast protons and beryllium that produces neutrons and boron, specifically focusing on the neutron. We found that this neutron emitter was the primary and dominant neutron emitting reaction in our experiments. And as you can see here in the table, the computed neutron rates of emission from our integrated modeling are basically of the order of the reactions or the measurements that we've made based on fission chambers. Now, the two interesting results that came out of this is that we can actually calculate the neutron emissivity profiles from a proton beryllium neutron, a primary neutron emitter, which is shown on the left-hand side with a cross-section of a jet. You can see that this has a really peculiar hollow on the axis and pushed to the off-board side neutron emission, which is purely driven by the fact that the threshold for this reaction is 2 MeV, and the only place where these protons actually exist, they're RF accelerated, are on these extremely wide, trapped orbits here on the outboard side. And the other result was the neutron energy spectra. So again, a peculiarity because this is an endothermic reaction, which means that the neutron energy spectra emitted from this primary reaction will start at 0 MeV as opposed to, the Q value of the reaction, and then is very broad, owing to the fact that we had, MeV range protons triggering this neutron emission all over the cross section of the reaction, and then tailing off, as you can see, at sort of really high energies. What we've done as the final step is then also compacted all of the calculated neutron emissivities from all of the fusion chain and compare this against our measurements of the fission chamber, all of this shown on the left-hand side. So 101, 184, and 101, 185, the top two panels are from a helium discharge, and 105, 453, the bottom one, is from a deuterium discharge. Things that something that I don't really have time to go into, but also in a deuterium bulk plasma, we've managed to create conditions in which proton beryllium fusion was still the dominant neutron emitter and fusion drive. And we've done a comprehensive uncertainty analysis of all of our integrated modeling contributing to this neutron yield, which brings us to just above 30% and an excellent match against the measurements. And then my last physics slide is basically, what about proton boron, right? So what we said, obviously, as we were doing these experiments and the analysis was ongoing, is, ITER changed their mind about the beryllium wall and ditched it for a full tungsten wall. But we know that there will be boronization happening within the ITER plasma or ITER sort of prep phase as an oxygen getter. Now, this gives us an opportunity to apply the methodology that we have developed to study proton-boron fusion. Why is this relevant? Because in early phases of ITER operation, we can actually drive a fastly energetic population of fast protons, and due to boronization, have boron present in the plasma, and again, trigger these reactions, trigger the tri-alpha reactions, and study, fast alpha confinement early at ITER. So what we've done is we've proposed these experiments at JET as well. Sadly, JET closed down before we could actually run these experiments, but then we just ran an integrated modeling analysis saying, what if we replaced beryllium with boron? What would we have measured? And we've done the same exercise. So first of all, we've calculated the source rate here on the left-hand side of the alphas emitted through the primary tri-alpha reaction, which is shown on the left-hand side. So this would be, again, the radial distribution of your alpha source. First in solid stemming directly from dress. So this is the source, and then slow down with a dashed line. And then we've also assumed a alpha tri-alpha spectrum, which is shown here on the right-hand side with the solid curve, and then slow this down in locust as well to get a relaxed distribution function. And then we said, well, how many alphas would we have produced in JET? And would we have potentially measured the secondary interactions between alpha and boron through the neutrons and gammas they've emitted? And the answer is yes. So the tri-alpha source that we would drive would be on the order or equivalent to that that we drive with D-helium-3 reactions, fusion reactions. So it's comparable to that. So an extremely powerful alpha source, which we could have detected at JET. And also the emissivity rates of the gammas and the neutrons are just on the lower side of what our gamma spectrometers and neutron fission chambers are actually capable of measuring. So would we have done those experiments? I think we would have sort of managed to measure those reactants. And to conclude, so I've presented the experiment. We've developed a scenario in helium and D at JET using HRF minority heating with dominant proton beryllium fusion and neutron emission sustained over several fast line slowing down times. And we had an extensive suite of validated diagnostic measurements to support that this was indeed proton-beryllium dominant fusion and providing modeling input. What we've done for the modeling perspective, we've developed this high-fidelity modeling of multi-stage fusion chains between fast ions and plasma impurities. We've applied it to proton-beryllium fusion, but as you can see, it can be applied in principle to any. This is done with Transjetto, Locust, and DRESS. The HRF minority distribution function was optimized with Locust and validated against field. So I cannot emphasize enough how important it is that we have a reliable assessment for the fast proton distribution function. The primary beryllium proton fusion was found to be the dominant neutron emitter. We've calculated the total neutron yield and validated this against the fission chambers, and we've demonstrated this application to a potential proton-boron fusion. And with this, I'd like to thank you for your attention and point you to the proton-beryllium experiment and modeling paper that was literally last week published in Nuclear Fusion. Thank you.
Okay, thank you, Zika. Now is the question and comment time. We still have 7 minutes. So any question or comment?
What proportion of the total proton population were these high energy MEV protons?
Sorry, the room mic is really poorly placed. So if the chair could repeat the question, I would very much appreciate it. I didn't catch that. Sorry.
Okay, I'll try and repeat it. What proportion of the protons in jet were at these very high energies?
Right. Proportion I don't really have a number in mind, but let's put it this way. So the proton distribution function is published in the nuclear fusion paper. So you're more than welcome to check that proton tail. But of course, overall, not a large portion of the protons that we've accelerated will actually reach above the 2 MeV threshold, which we need for the primary proton-beryllium neutron emitter. Yet we had plenty of neutrons. The proton distribution function will fall over several orders of magnitude as we reach high MEV sort of energy values. But I can, dare say that it would be on the order of % of the total density of hydrogen. So meaning that was a % level. So most likely, on the order of 10 to the minus 4 based compared to the main ion species.
Okay.
Thank you.
Thank you. Any other question? So if no question, we thanks Zika again. Yeah.
Thank you very much.
Okay, next speaker is Tala Ahmadi from University of Tokyo. His presentation talk is 3D kinetic initialization of proton boron field reverse configuration with neutral beam boron fast ion current. So Tala, can you hear me?
Yes, can you hear me?
Yeah, we can hear you. You have full screen your presentation.
Yeah, a moment, please. Yeah, is it all right?
No, still. Let's see. It's okay. Go ahead. Yeah, please. Yeah.
Sorry, for some reason doesn't work. Okay. Yeah, so thank you very much. Hello, everyone. My name is Tara Ahmadi. I'm from University of Tokyo. I would like to thank organizer for allowing me to give an online talk. I'm sorry I could not attend in person. My talk is a little bit different from the previous presenter. I'm gonna discuss fully the kinetic modeling of proton boron situation in FRC plasmas using 3D kinetic modeling. So let's start just to briefly discuss what is FRC. FRC is like field reverse configuration. It's like a compact tokamak, but without external toroidal magnetic field. There is a strong toroidal plasma current that produces a strong internal magnetic field opposing what poloidally injected into the chamber. So our actual magnetic field gonna have opposing magnetic field in radial direction. That's what we call field reverse in the FRC situation. So why FRC is interesting? Because it can operate in high beta regime despite having a linear simple structure. And it has an open-end diverter to remove excessive energy and particles. So currently, multiple FRC devices operate using neutral beam injection for heating, for current drive, and for stability. So the physical question is, what is the effect of NBI in PBFRC? So what we know so far about the effect of NBI is that NBI produces fast beam-borne fast protons that they join background plasma interacting with the particles. So what is important that is in FRC, the maintaining equilibrium is very important due to the lack of external toroidal field. Therefore, NBI proved itself to work in this direction very well, but we are still not sure how it maintains the equilibrium because these beam-borne fast protons produce a current, but this current does not correlate well with the stability that it provides. So it needs to be regulated, and we need to provide scans if we're gonna give engineering level suggestions. Yeah. So what is probably happening is that the NBI provide raw beam, but the background plasma, especially electrons, try to cancel that current through the return current. Therefore, what is necessary to be discussed related to the relationship of magnetic field and NBI is not the raw beam current, it's the survived current after the interaction with the return current of the FRC itself. So what is the relevance to the PB structure is, can this NBI firstly support the unstable magnetic structure? And secondly, can this NBI also provide some more opportunity for improve the fuel density in these structures and how it's gonna be? So what I suggested in this case, I'm using a 3D VPIC. So we're gonna have 4 groups of particles, electrons, protons, borons, and beam-borne protons. So it's a 3D structure for initial setup. I used a very thin equilibrium FRC that you can see here. The field reverse is clear, and you can see how thin it is, which confirm that how unstable it can become. It can tilt, rotate, and collapse very easily if we do not maintain it. Yeah, so some words related to current decomposition. As I already mentioned that we're gonna have beam-borne fast electrons, then it's gonna dynamically get affected by the current that is provided by the background plasma. This current remove some of the effect of the initial NBI current. Then we're gonna have surviving net currents that gonna affect the magnetic, that gonna coupled with our magnetic structure. Here we defined D reversed, which is the depth of the negative side of the magnetic structure, which is necessary to maintain a stable FRC. So this is where our ion and PB equilibrium looks like, and here is the beam-borne channel in the same snapshot you can see. Yeah, so before going forward, I try to make a scan to understand the relationship between the injected beam velocity and the how much of the survival current's gonna be. So you can see that such maps are very important in understanding a regime before committing to any experimental activities. And we realized that we need to define something called F effective, which is the fraction of the NBI current that survives after cancellation. So from here, we're gonna discuss in this regime. So now the main result, the first part gonna be related to stability of the magnetic configuration. We have six cases. Same initial conditions, but what is different is the electron response to the NBI current. So you can see that you can see the time evolution, and F effective, which I mentioned, is the fraction of the survive NBI current that's gonna couple with our magnetic configuration. So what we realize is that increasing this F effective shows that the D reversal gonna be more, fairly by 1 order of magnitude. Therefore, more survive current from the NBI we have, stronger our FRC gonna be and more stable, which is what we need to maintain, to start any fusion reaction. Before starting any fusion reaction, we need such a situation. So here you can see two cases. It's the first case is where there is no current left. There is no improvement in the magnetic configuration, and here you can see the high improvement in the reverse configuration. You can see the total toroidal current and the beam-borne toroidal current and the co-location relatively at this and at this location. So this we confirmed that if we want a stable FRC, we have to improve the survived current from NBI. Yeah. So in order to, this is just a quick test. I just checked that what will happen if instead of constant NBI, I use the pulse NBI. You can see we have the turn-off moments, and at the turn-off, the improvement of the magnetic configuration decreased 15%, while we only lost 13% of the retained fast protons. Therefore, we can conclude that what is necessary is not just the raw particles, it's the particles that can couple with the magnetic configuration. So now, what is all this relationship has to with the BP structure? Here you can see the magnetic structure from a later time when we have relaxation in a strong magnetic enhancement. The blue line is where the main bulk PB overlaps by the density, and the orange line is where the beam-borne protons overlap with the borons, background borons. So what we realize from this is that majority of background or bulk protons react and co-locate with borons in the positive side of the magnetic field. However, whatever was retained from the beam co-locates with borons in the negative side. The negative side is the side that we try to keep and enhance through the NBI in this configuration. Yeah, so you can see that it is it's also the NBI reacts with the proton structure in the background. So now I separate magnetic control from the global field rearrangement across the 6 dynamic comparison cases that I already showed. The magnetic reversal increased by 17 times, correlating with the survival of fast protons. However, if you check the proton boron overlay, you see that if we increase the magnetic coupled protons, it does not really affect the proton boron overlay, which shows that we are able to use NBI to enhance our magnetic structure without damaging or disrupting the proton boron fuel configuration. So this part is interesting because the question is then what affect the proton boron in a FRC, in a weak FRC plasma? So the question is probably the velocity of NBI. Here we checked several parameters for different NBI velocity, and then I defined the proton boron accessibility per beam energy and compare it with the magnetic support that I already discussed. So it seems like a slower and NBI beam, more magnetic support it can provide for our unstable plasma. However, it doesn't work like that for the accessibility because for proton boron reaction, collocation is not the only necessary option, is not the only necessary requirement. What is important is that these particles also locate in the similar energy range. So this energy range will be achieved only for high value of NBI. So in this case, it's like 0.022 C. We could achieve a relatively reasonable accessibility between proton and between the fast retained protons and the background borons. And you can see that for the chosen energy range, we had from like 0% for this level and increasing it to around 20%. Unfortunately, in this way, we are losing the magnetic support that it was being provided. So generally, it seems like there is a trade-off. Lower beam energy is economical for the magnetic support, but higher beam velocity opens more PB accessibility. So there is no single setting that improves reaction and magnetic structure. So it's important to study these cases and optimize for proton boron FRC structure. I should note that NBI is not only used for stability, we are also expect to see some heating, but in this case, the model is reduced. We did not include slowing down and transport. Therefore, it might not be appropriate to study the heating itself. But within the discussions, within the collocation and energy range, I guess we are okay. Yeah, so this is the conclusion. We confirmed that it's possible to use FRC for NBI reaction. It's possible to make it stable by using NBI, and also NBI affect the PB situation and reaction and related to the captured protons. Yeah, thank you.
That sense, kind of no is question or comment time. Any question or comment? Oh, okay. I have a comment or question. So, recently I read a paper from the famous FRC company TAE. In their paper, they decide they use NBI, just use NBI to form the stable FRC plasma. So, to compare your simulation with their experimental result.
Yes. So that is correct because tri-alpha is using the same logic. They are having an unstable, weak FRC, and they try to improve the stability by using the NBI. However, what I read in the paper and what I know about the experiment is that it is not properly optimized, and increasing the size and configuration of FRC really needs a more complicated NBI injection. So it should be either a long pulse or a short pulse or different configuration. So yeah, we are in the same direction, but using the proton boron.
Okay. Thanks again. So
yes, thank you so much.
Yeah. So if no question, we start the next presentation. Next speaker is Dr. Xie Huashen from Beijing Velo Alpha Technology Company. His title is Development of Reduced Multi-Fold Equilibrium Models and its Application to the Proton Boron Spherical Top Mass. Yeah. So, Tala, you can stop your share presentation, yeah.
I already did.
Yeah.
应该已结束。
Okay. So.
Thank you. I will introduce our recent work on develop a new reduced multi-fold equilibrium model and its application to the proton boron sulfate top marker. It's mainly for the EHL2 and EHL3B, and we're trying to figure out how this effect can be. So. I will first give you some background information from the history of the multi-fluid equilibrium model, and then I will introduce our new model and the result for EHL2 and EHL3B, and finally I will give a summary. The multiple equilibrium model it means that the force balance between the thermal pressure and the electromagnetic force of each species in proton boron sulfate top mass. Strong rotation can separate different species, including the proton, boron, electron, and fusion product and impurity. For this case, the sample fluid MHD description may not sufficient for this. There are many, actually, 40 years ago, 40 years ago, there are many works on relative of this topic. The most straightforward model is just reduced from the multi-fold equation and remove the time depends part and then yield the equilibrium part. This is the most straightforward version, but this is difficult to numerical solution. So the existing modeling are usually either too complicated or too simplified to get the essential physics. In this work, our goal is to find a practical, useful equilibrium model for proton boron sulfate top marker that should retain the essential physics, but without too complicated for numerical solutions. If we only consider the sample fluid MHD toward rotation, actually there are many work on this. For example, these two papers. This is for the MHD fixed boundary condition toward rotation solution, and this is the free boundary, and this is straightforward.
The limitation is that they cannot distinguish the central the separation between different species. So all the ions electron are in the same fluid. There are also other works relevant also to protoboron. Also F1ST equivalent. This is a famous work done by Travel team. They study both FRC and sulfur. Actually, I think this is a good motive for the modeling. They have included many essential physics and remove some not important physics. But I'm not sure why this model not widely used for the work. I think it's still complicated, so not too many people really use this model. There are also some other model. I think the most comprehensive used model is Ishita's model. This Martin Peng several years ago used this for EN's machine for also for the experimental. I have also tried this modeling. This can be very general to multi-species, but the limitation is that usually for one experiment result fitting, we need maybe half an hour or much more time to get a converted solution. So this is the reason is that there are too many free product functions. For example, the density and the temperature and also other product functions. So this is still complicated for faster experimental fitting. The flow 2 model is actually many people are studying on this. This is 20 years ago by MIT team. They also said that yeah, this is good for academic use, but in experimental application, they are required extensive trial and error. This is said by the authors. So this is still not good for experimental. After we know this background information, then we think how to develop and minimize the models. We need to return the multi-species effects and the total rotation, but we do not hope it's too complicated to numerical solutions. So also this model should can reduce to the M3 model easily, and also including the electrostatic potential dependence of density equation. This is just algebraic equation and easy to solve. This we should balance the complicated and the essential physics. Then we check tone patterns. For example, the Pareto current, we must have this. This in M3 is F% in M3 equation. So we should keep this. But we do not keep the Pareto rotation for each species because this will make the model too complicated for numerical solution. So and also this because this rotation is small, so we can just omit it at this stage. The total rotation and the charge separation is essential for the high rotation cases. So we should keep these two terms. And the pressure anisotropic is not a leading order, so we just omit this. The multi-species effect we should keep it. For the drift magnetic surface, I have checked this with several parameters. We find it's also a small order, and then I omitted it. For simplification, we also just keep the plasma only inside the last cross surface. When we keep only these essential models, we find the model can be just slightly extended from the M3 order model. Just only this equation are exactly the same as the M3 equation, and this is also the same. Only the pressure term is have some modification from the M3 model. And this pressure is from the density and the temperature of each species, and also including the rotation effects. We can use this simple profile function, and the easy to set the parameter, and also the only added profile function for each species density, temperature, and the total rotation. And this work I have published recently. So for more detail of the model and the numerical solution, one can read this paper. Then we can check whether this model is correct. So and whether it can be reduced to the M3 model, and how the effect of multiple effects can be. This is a benchmark of the without the rotation, and this can reduce to the sample freedom model exactly. We have two code to benchmark, and it's the same. If we have the rotation, and we can find that the density will be shifted to the low field side, and there are also some electrostatic potential. This model can, if we only use the simple final differentials in the RZ grid, is still very robust, and the computer time is around several seconds. This is easy to solve. Further later will show that this can be more faster. And further, I discussed the module result we obtained. This is tested for the actual two parameters. The temperature around TE around 10 keV and the TI around 30 keV. We can adjust the rotation parameter. This one is without rotation, and this is just exactly the M3 case. And we included the rotation. We will find that this is density profile of each species, and it will be shifted outside. When the rotation is this Maho number is around larger than 2, and we can find that the density will shift outside. Will shift outside to the low field side. So this is the rotation effect, and also we will find that the electric potential will be around. For this case, is around maybe this is around 10 kilowatt. So it's a huge case. This means that if the rotation is small, actually this effect is not small. Depends on the Mach number. If Mach number is only when Mach number is around 1 or larger than 1, this effect will be important. We also check the actual 3B, and this is similar result about that. If rotation is very small, and this density not shifted too much. If the rotation is large, this Mach number is around 2, and then we'll find a large shift outside, and also the electrical potential. So we can open the module conclusion that the equilibrium change are weak below Mach number below 0.5. When the Mach number is larger, then the rotation and the charge separation requires more for the treatment. This is why in usual case, why M3 equilibrium is still very good for experimental, because the Mach number usually is not small, not too large. But when we study the reactor scale, when the rotation is large, then this effect we should include. The model is easy to solve for the final deformation. Recently, we also try our new VQ machine. We found that this can be reduced to can be solved in millisecond, and we use and agree with the hybrid solution well. And for this, we have done comprehensive parameters again for the how this effect affect the fusion power and the radiation and also other physical parameters. If you are interested, you can refer to this paper. For a summary, we reduced the multi-field model for proton boron surface tokamak equilibrium. Actually, this is not limited to this proton boron. Also can be DT fusion, also some heavy impurity. And this can return the dominant toroidal rotation and charge expression. And this can recover the single-fluid MG limit easily. This can provide test baseline for the rotation proton boron surface tokamak equilibrium. In the near future, we can extend this to the construct equilibrium fitting of the experiment data and also for integrated modeling. And also we have we are beginning to study stability and also transport effect. And in the future, maybe if it's important, we can add this anisotropic and drift surface and free boundary extension. Thank you.
Question time. Thank you for interesting presentation. So I have a question on the rotation.
Yeah.
So in your nice simplified analytical equilibrium model, still you kept the multi-species division, of course, also to the rotation part. And then I'm curious, because to my knowledge, what I heard from experimentalists is that, for example, even in present day tokamak experiments, it's very hard for them to directly measure, for example, main thermal ion rotation. So instead, they assume that in many cases, the carbon impurity rotation profile is similar to the main thermal ion. So this is an example that I heard from experimentalists. So I'm curious, in practical situations, how we get different rotation profiles of different species, all different species, including fast ions and electrons.
Actually, this is not needed to different profiles. If the rotation is the same, the Mach number is different. And the Mach number is most important for each species.
So in this model, are you presuming that all the profiles of the different rotation the rotation profile
it can be set up by the user. You can different, you can the same. Depend on it can be sent to different profile, also the same profile.
Yes, so I was curious what
is
I'm curious about the future. So how we use this?
Then we can measure for the experimental and give the profile for the input of this model.
So maybe you can guess and reconstruct different rotation profiles based on different.
Usually, it maybe compare the measurement and also the transport analysis.
Okay, thank you.
We still have 4 minutes. No question. Thanks. Speak again. I have one.
Professor Xie, very nice talk and work. So I have one question is that regarding the charge separation, so the radioelectric field is naturally generated through the ambipolar transport between electron and the thermal ion species. So I want to ask, so whether the radioelectric field is incorporated in the unknown EQ model.
This is just for the quasi-neutral condition.
Okay.
For this we can solve the electric potential.
I understand. Thank you.
So that's okay. Next speaker is Professor Liu Wang from Jiangnan University. His title is Initial Monte-Carlo shell model approaches to low-energy nuclear reaction for advanced building frameworks.
Okay, good afternoon. I'm Lang Liu from Jiangnan University. Actually, this is the first time for me to attend this wonderful symposium. I would like to thank the organizers to give me this opportunity to introduce our work from the nuclear structure point of view. So the title of my talk is Ab initio Monte Carlo shell model to nuclear reaction for advanced fusion frameworks. So in this symposium, we discuss a lot of this reaction. And we know the reaction cross-section is one of the most core physical quantities for proton-boron fusion. And we know the precise nuclear structure information is also crucial for this reaction. We know from the yesterday Professor Pang Danyang's talk and other talks, they say, for example, nuclear structure wave function input is very important. So we know that the accurate reaction cross-section requires precise nuclear structure information. We need precise nuclear structure input. Okay, recently based on the low energy QCD, the accurate realistic nuclear forces can be obtained by the Carroll perturbation quantum Monte Carlo, local shell model, nuclear lattice simulations, coupled cluster models, and Monte Carlo shell model, and so on. So for nuclear shell model or local shell model, it can be looked at as exact solution. If you have a complete set of bases, then you just simply expand your Hamiltonian in this basis, so you can get the exact solution. So only thing you needed to do is to solve the eigenvalue problem of this large Hamiltonian matrix. So, but the problem is for nuclear system, the dimension of this Hamiltonian matrix is extremely large. Usually, the dimension is about 10 to the power of 10 or even larger. To overcome this difficulty, the Monte Carlo shell model was introduced. So, because if we only interested in the ground state or the low-lying excited states, we found not all the bases are important to describe the system. So, if we find some way to get the important truncation, we can get some important bases. Stochastically, this basis can be selected stochastically. So by this selection, the dimension of Hamiltonian matrix can be reduced from 10 to the power of 10 to 10 squared or even smaller. Okay, so the central Monte Carlo shell model idea is importance-driven basis construction. So first we generate deformed slight determinants, and then we project this determinants to required angular momentum and parity, and then we select the basis wave function by energy gain
by lower the variational energies. And then you get a set of bases. You simply diagonalize the Hamiltonian in the selected bases. And then the system wave function is a mixture of these bases. So this mixture can be a deformation mixture or configuration mixture. For the interaction, the chiral interactions become tractable through some transformation. For example, unitary correlation operator method or similarity renormalization group method. So we put as a chiral effective nuclear-nuclear interaction as an input interaction, and then we transform this interaction by UCOM or SRT or in medium SRT, and then we write this interaction in the harmonic oscillator basis to get the matrix element, and then as this matrix element as an input to the Monte Carlo shell model calculation. So the wave function of Monte Carlo shell model is a linear combination of the project slider determinants like this. So the NB is the number of the slider determined basis states. We call this Monte Carlo shell model dimension. And this the deformed slider determinants can be written in this form. So which is parameterized by a complex matrix D with orthogonal condition. So this matrix D was generalized by a Monte Carlo sampling with a stochastic technique. And then the energy eigenvalue and the coefficient are obtained by solving the following generalized eigenvalue problems. So I will show you some result as an example. So this is calculate the energy and quadrupole moment of Boron11. So you can see the convergence of this calculation is very good. So this is excitation energy and the total energy as a function of the Monte Carlo shell model dimension. And you can see the dimension is about 35. We can already get the good convergence for the ground state and some excited states. And also for the observables, we can get a very good convergence for the quadrupole moment. And we also investigate the transition probability. For example, we calculate the E2 transition. We calculate the BE2 from the first two state to the ground state, and the second two plus state to the ground state. And we compare to the experiment data. We find we show a good accuracy to compare to the experiment data. And we compared our calculation result with other ab initio calculation, for example, the green function Monte Carlo and the local shell model. This is another example for lithium-7 and lithium-9. So you can also find a good convergence for the 1/2 and 3/2 minor state for lithium-7 and lithium-9. And also the good convergence of the quadrupole moments of as a function of the dimension. We also calculate the magnetic moments for lithium-7 and lithium-9. This is our calculation results. They show a good agreement with old experiment data and the new experiment data. So as I discussed in the previous, we say the total wave function is a mixture of different deformation. So this figure is energy surface in beta gamma plane. So you can see, for example, this is ground state of nickel 68. And we know the ground state of nickel 68 is a spherical shape. But in our calculation, you find some circles. Each circle represents
each wave function basis. Okay, so the size of the circle means the probability of this basis of this base. So you will find even we know the ground state of nickel 68 has a spherical deformation, but in our calculation we find they still have a very small possibility to locate, for example, in the oblate shape, and some even smaller probability in the prolate shape. Okay, so we can also find for the sigma 0 plus state, we know this state is oblate shape, but in our calculation, we also find they have small probability located in a spherical shape and some small probability located in prolate shape. Okay. So, and for a microscopic theoretical model, I think one of the most important things is you should tell people what is the accuracy of your model. Okay, so if people ask what is the Monte Carlo shell model error, so we can calculate the energy variance following the basic quantum mechanics concept. So we can calculate this energy variance following this equation, for this formula. And we only need to do to calculate the matrix element of this H square in the slide determinants. Because this is calculating is very time consuming, I will just show you a very simple example of helium-4. So you can see we calculate the helium-4 in two major shells, and with the increasing of the Monte Carlo dimension, you can see the energy variance become smaller and smaller and reach 0. So that means we get an exact solution. If we benchmark our result with shell model, we can see this is the shell model calculation of the energy and occupation number for different single particle states. And we can see with the increasing number, with the increasing of the Monte Carlo shell model dimension, and we can reproduce exactly the shell model result, both for energy and occupation numbers. And usually, even if you don't get the energy variance reaches 0, you can also get perform an extrapolation of the energy variance. You can see this figure shows the total energy as a function of energy variance. In these papers, they say if you extrapolate the energy variance, you also can get a value, energy, which is very close to the exact shell model result. Okay, now I think this result is you may have interested in. Very recently, the first principles Monte Carlo shell model realization for carbon-12 Hoyle state can be is done in this paper. In this paper, I think they calculate the carbon-12 for the ground state and the second 0 plus state. This is Hoyle state, and the third 0 plus state. And you can look at the second line. So this means in the calculation, they find for the ground state. Usually we think the ground state of carbon-12 is not alpha cluster structure, right? But in the calculation, in the ab initio calculation, they find even for the ground state of carbon-12, they have 66% alpha cluster structure and 94% other configuration, for example, single particle configuration also. And for the Hoyle state, you see, the calculation shows they have
61% 3 alpha structure configuration and 33% other configuration like this. So this is very interesting because in the at the beginning of our calculation, we don't assume any alpha cluster configuration or any deformation. We just use the Monte Carlo shell model ab initio calculation. We get this type of configuration mixing. Okay, so let's give a very short summary and outlook. Here, I think the Monte Carlo shell model is an ab initio model with controllable errors that can provide nuclear structure information with controllable precision. And the nuclear structure with the Monte Carlo shell model to the proton-boron reaction cross-section calculation is promising. And of course, we still have a lot of work to do. For example, we need to take into account the continuum and also other aspect. So this is our collaborators, and thank you for your attention.
Very interesting. Question one, you are using UCOM.
Yeah.
For to adapt your chiral interaction. So, but during your benchmark, you don't have very good binding eligible.
拜。